but just as a quick note, under me, you should see a button labeled tonight's resources. If you click that button, that should take you to a page with resources for tonight. That includes things like the slides, note sheets, any of those sort of things that you'll need. You'll see the chat on the side where you guys are welcome to talk and chat and talk to each other throughout the night. There is a Q&A, which allows you to ask questions to us, and we'll be answering throughout the night. Polls that, if you want, you can answer throughout the night and talk about your favorite Sour Patch flavor or how everyone's feeling. And yeah, so without further ado, I am just going to pass it off, and we will get started up with Unit 6. Which I think we need to get the slides up.
All right, what's up, guys? I'm Jahangir. I'll be teaching Unit 7 for the slides today. And I'm from Texas, so if you guys are from Texas, drop it down in the chat. And I'm glad to teach Unit 7, and I'll pass it down to Arnika.
Hey guys, I'm Arnika. I'm going to be going over the first unit of today, Unit 6. And I'm a junior in high school. For those of you who don't know, I took AP Chem last year and I loved it. I'm going to pass it off to Shreyas, who's doing Unit 9, to introduce himself.
Hey guys, my name is Shreyas. I'm a senior in high school and I live in Connecticut. I'm going to be attending Northeastern next year. I'm going to be majoring in biology. I took AP Chemistry in my sophomore year about 2 years ago, and I thought it was a really fun class. And I am your Unit 9 specialist.
All right, so let's get right into Unit 6, which is Thermodynamics. Okay, so to start off, physical and chemical changes. So physical changes are basically anything that involves intermolecular changes. So this can be things like water melting and ice freezing. And this is basically always indicated by changes in temperature. And chemical changes, on the other hand, involve the forming and breaking of ionic and covalent bonds between elements. So this is like an irreversible change. It can be things like baking a cake, because after you bake a cake, you can't really unbake the cake. It's going to be a constant and a permanent change. And another thing is like heating fire, because when you heat fire, you can't unheat it. All right, so now for kinetic energy and potential energy. We talked a little bit about kinetics yesterday, but kinetic energy is basically the energy that results from the motion of an object. And you should know that temperature is directly related to the average kinetic energy. So what this basically means is as temperature increases, your gaseous particles are going to move faster. And to represent the kinetic energy, there is an equation. It's called 1/2 mv squared. And in this, the mass is basically m, and that's in kilograms. And v represents the velocity, and it's in meters per second. As opposed to potential energy, which is basically the stored energy in an object based on its position. So basically think of it as the bond energy between atoms and molecules in chemistry. Potential energy, there's a form called electrostatic energy, and this is basically the result of the interaction between charged particles. An example of electrostatic energy for chemistry is the Coulomb's law, which we did talk about yesterday, and this is basically, to go over it again, electron potential energy is equal to Q1 times Q2, which are the charges, divided by D. Okay, so for the law of conservation of energy, this is basically one of the fundamental concepts, and it basically just means that energy can't be created or destroyed. It can only be transferred between different forms of energy. So what this means is that the total amount of energy in a closed system, I'll be talking about what a closed system means in a little bit, that's constant. So in chemistry, in a chemical reaction, the reactant potential energy is basically converted into the the product potential energy, but the total energy remains the same. So nothing's being created or destroyed in this process. It remains the same. Okay, so now I'm going to be talking about the energy changes and the system and the surroundings. So the system plus the surroundings equals the universe. The system is basically anywhere that the reaction actually takes place. This is like the beaker of an object. So if the reaction takes place in a beaker, then that would be your system. There's different types of systems. So first, an open system, which basically allows air, heat, energy from the surroundings into it, and it usually takes place in an exchange system. You can see the picture on the bottom of it. And yeah, so for a closed system, on the other hand, an open system with a stopper so that the air can't be transferred in and out, and only heat is able to transfer. And an example of this is a thermos, because it's basically an open system that has a lid on it. Oh yeah, and for open system, a pot of water on the stove, because the heat and the air, the steam are allowed to transfer between the surroundings and the pot, but everything is allowed to transfer. And for an isolated system, it's completely covered on all sides. It's completely isolated, so nothing is allowed to transfer. So one example of this is a sealed container filled with gas, or a calorimeter. I'll be talking about calorimeters a little bit later. And the surroundings is basically everything else around the system. All right, so for endothermic versus exothermic, basically just know first that the enthalpy is represented by H, and enthalpy is basically the total heat constant of the system, and enthalpy is really important to know for Unit 6, so make sure you do know it, and delta H, which is the change in enthalpy of the system. So for endothermic processes, it's basically when there's a positive H because the system is gaining heat, and the heat travels from the surroundings into the system, as you can see in this picture, where the heat is coming into the beaker. And for exothermic, it's a negative delta H, which means that the system is losing heat. And you can remember this by, I remember it as exo. I know it's a little silly, but yeah, it helps me remember it. And this basically means that the heat travels from the system into the surroundings. Okay, so for energy diagrams of reactions, energy diagrams basically represent the change in energy in a chemical reaction, and this basically shows the potential energy of the reactants and the products, and the activation energy required for a system to occur. So as you can see for exothermic, this basically has a higher potential energy in the products than in the reactants, and this is a higher activation energy. And in endothermic, there is a lower potential energy in the products than the reactions, and a lower activation energy. I think these might have been switched accidentally, my bad. So the first one would actually be endothermic, in which that the higher products is in the products than the reactants, and that has a higher activation energy. Sorry for the confusion, but yes. All right. So for the collision theory, it's important to know that the rate of a reaction is proportional to the rate of the collisions, and the orientation matters for the reactant molecules colliding. Because if the reactants are both like this and they're supposed to be like this, then the reaction can't occur. So increasing the temperature or the concentration of the reactants can make the reaction actually go faster, and this basically increases the amount of energy of the collision. And the proper orientation plus enough energy for the reaction to occur makes a successful collision. All right, so now we're going to be talking about calorimetry. So calorimetry is basically the study of heat flow and exchange between a system and the surroundings, and this is used to calculate delta H. So for the coffee cup calorimeter, which is a simple calorimeter, the reaction heat is used to raise or lower the temperature of the surrounding water. I see in the chat that the graphs are right. My bad for the confusion, they're actually right. I'm sorry about that. So for the coffee cup calorimeter, the reaction heat is used to raise or lower the temperature of the surrounding water. And the temperature change of the water plus the mass and the specific heat means that the heat of equals the heat of reaction. So in this coffee cup calorimeter, you don't really need to know exactly what's in it, but it's good as to know for the concepts. So you have the stirrer, you have the thermometer, you have the insulated stopper that makes it a closed system, and then you have the nested isolated cups and the reaction mixture. Okay, so this is a really important equation to know for AP Chem. It's called Q equals MCAT. Q is basically the heat in joules, and M is the mass in grams or kilograms. And usually it's in it's usually in grams for AP Chem. And C is basically the specific heat of the substance. The specific heat is usually given to you, and you don't really have to notice on your own. So don't worry about like memorizing the specific heat. And delta T is the change in temperature in Kelvin. So if it's in Celsius, you would have to change it into Kelvin by adding 273.15. So the specific heat is the amount of heat that's required to raise the temperature of a gram by 1 degree Celsius. So the higher the specific heat, the more energy it takes for the object to heat up and cool down. Okay, and now it's time for a brain break. So you guys can drink water. I have my water with me right now, and we'll just be chilling for about 2 minutes. If you guys want to say anything in the chat, please let me know. But yes, 2 minutes from now. All right, guys, so that's the end of the break. I see a bunch of things in the chat about breaking bonds and adding energy, and I'll be going over that in just a little bit. Okay, so before that, I want to go over something called phase changes and energy. So as you can see in the progression of the reaction on the left, this is basically the progression from a solid into a gas. So you can see the different changes between the states from solid, liquid to gas, and the intermediately the plateaus between them, and those are called the melting and the vaporization points. Melting is from solid to a liquid, and vaporization is from liquid into a gas. So as you introduce heat into a system, this system goes from a solid to a liquid to a gas, and you can see this in the graph right there. During the transition from one state into another state, additional energy is required to heat or boil the substance completely. And these are called the heats of fusion and heats of vaporization. Heat of fusion is when you melt it, and heat of vaporization is when you actually vaporize it. So to transition, you need the appropriate temperature and the required energy. From a solid to a liquid, for example, the solid will remain at 0 degrees Celsius until it has completely melted before the curve progresses. So that's why you can see the plateaus, because it hasn't completely melted until you can see the curve going upward into the liquid. Okay, so now we're just going to try an example problem. You guys don't have to do it along with me, but you can just follow along while I explain how to do it. So how many joules are required to change 30 grams of ice at negative 20 degrees Celsius to steam at 140 degrees Celsius? And you're given the specific heat of ice, the specific heat of water, the specific heat of steam. So those are the 3 different states that you have. And then the heat of fusion for water and the heat of vaporization for water. So those are good things to know, because that's all you need to know for actually doing the problem, which we're going to do right now. Okay, so to solve it, you need to actually account for all the different changes in the states. So you have the solid, the melting, the liquid, the vaporizing, and the gas. So for the solid state, liquid state, and the gas, you basically want to use your Q equals MCAP formula. And so let's take solid, for example. To find Q, you want to do 30 grams, which you're already given for the mass, the 2.108, which is basically the specific heat which you're given. And then the 20 degrees Celsius, I got that by doing negative 20 degrees Celsius, which is the temperature, minus 0 degrees Celsius. And 0 degrees Celsius is basically the melting point of water. And after you multiply those all together, you get 1,264.8 joules. And I see Jahangir has joined me on stage. Hi, Jahangir. All right. And then for the melting and vaporizing states, you basically just want to do heat of fusion times the mass and the heat of vaporization times the mass, because these are intermediary stages. So let's take melting, for example. You just have 334 joules by grams times 30 grams, and then the grams cancel out. So all you have left is joules, which is the energy that you need. And then after you do all of this, you just add up all the different state changes, and then you get the total summation, which is 94 kilojoules. Okay, so for cooling curves, this is basically the same exact thing as a heating curve, except it's going downward instead of going upward in temperature. So this goes from gas to condensing into liquid, and then from freezing into the solid state. So this is basically downward instead of upward. And the heat of condensation and freezing are the negatives of the heat of fusion and vaporization. So if you don't get the condensation and freezing heats on your test, you just basically have to do the negative of the heat of fusion and vaporization that they give you. Okay, so these are good important concepts to know. These are the bond enthalpy and the bond dissociation energy. So for bond energetics, breaking bonds requires energy, and making bonds releases energy. And a good mnemonic to remember this, I remember this as BARF. So this basically is breaking, absorbing, and releasing, forming. So that means that breaking bonds requires energy, and making bonds releases energy. So for bond dissociation energy, there's energy that it takes to break a specific bond. So if you have more bonds, you have a higher bond dissociation energy, because, for example, if you have a triple bond, that's a heftier bond. So it takes a lot more energy to actually break that specific bond. And a longer bond, for example, like a single bond, that's a weaker bond. And a shorter bond will be stronger, a longer bond will be weaker. Okay, so for an enthalpy, sorry, can we go back a little?
Yeah.
One more slide. Sorry, one more slide. Thank you. So for an enthalpy of reaction, the bond dissociation energy can be used to calculate the right amount of energy, because the reaction is the breaking of reactant bonds and the forming of product bonds. And this can be represented with the equation, the summation of H broken minus the summation of H formed. So remember, the enthalpy of reaction is the reactants minus the product. I like to remember this because there's another concept that we'll be talking about later, which can get confusing because that's products minus reactants. But for enthalpy of reaction, I like to remember reactants minus products. All right, so we're just going to go over a quick example of how to find the heat of reaction, or the enthalpy of reaction. For this following example, it's CH4 plus 2O2 yields to CO2 plus 2H2O. So to do this, we want to use the equation, the summation of the H broken minus the summation of the H formed. So first we want to do the 4CH, and that's CH4. There's 4 of the CH4 elements, and they each have a single bond. Since there's 4 single bonds, you want to do, you basically just want to use the 413 that you're given and multiply by 4, because there's 4 single bonds. And then you add 2 times the double bonds of oxygen, because there's 2 double bonds, you do 2 times the 2 double bonds. And that would be 2 times 498. And then you subtract 2 times C double bonded with O, because in a CO2 molecule, there's basically 2 double bonds and there's 1 molecule. So you just do 2 times 799. And then you add 4 times single bonded to H. And this is basically 2 of them, because in H2O, there's 2 single bonds. And then you add up the reactants, and then you add up the products, and then you subtract reactants minus products to get negative 802. All right, so for the enthalpies of formation, the standard enthalpy of formation, which is the delta HF, that's basically the amount of energy it takes to form a compound. And like I said before, this is easily confused with the enthalpies of reaction, but for this one, it's basically H reaction is equal to the summation of N times delta HF of the products minus summation of M times delta HF of the reactants. So this one is products minus reactants rather than reactants minus products. And N and M are the stoichiometric coefficients of the reactants and the products. So this basically means how many of each product and reactant you have. And for an element, remember that the delta HF is always 0. So this is not given to you. You just have to know that this is always going to be 0. Okay, so for an example problem, we basically want to use the standard enthalpies of formation to find the change in delta H of reaction for the following reaction. And this is basically the same reaction as before. So, and then we get the table of the enthalpies of formation. So for this one, remember that this is the products minus the reactants. So for the products, we have CO2 and 2H2O. So for the CO2, we have CO2, as you can see in the chart. I think I did CO2 first, yeah. So that's negative 393.5, and you multiply by 2 because they're that's the negative 393.5 that you see in the second one, and that you multiply by 1 because there's one molecule of that. And then for the 2H2O, since there's 2 molecules of that, you multiply 2 times the enthalpy of formation. And then you add those 2 together, and now you go to the reactant side. So you do 1 times negative 74.8 because that's CH4. And then since I mentioned earlier that the elements is basically, they all have a enthalpy of formation of 0. So you do 2 times 0, so that's just 0. And then you basically subtract the products minus the reactants, and then your final answer would be negative 890.3 kilojoules per mole. All right, so the last major concept we're going to be talking about today is Hess's law. We did mention this a little bit in the last session, but we're going to go in depth on it today. So there's basically 2 types of pathways. One is pathway dependent, and the other way is pathway independent. So if the result of something depends on the order you did it, that's called pathway dependent. And if not, it's called pathway independent. Okay, so Hess's law basically is the change in enthalpy of a chemical reaction, and this is the same regardless of the way you go from reactants to products. So the enthalpies of formation for different reactions can be basically manipulated to get a single reaction that you want, and you can find the total enthalpy of that one reaction. Okay, these are some basic rules. It'll make more sense when I do an example of it, but these are the basic rules that you want to know. So when a reaction is reversed, the enthalpy basically stays constant in magnitude, but you flip the sign. So if it's positive, you make it negative. If it's negative, you make it positive. And this also changes the this changes the sign of the delta H from negative to positive and positive to negative. So if an equation is multiplied by n, which is any number, delta H also has to be multiplied by n. When two or more reactions are added, the individual enthalpy changes of each reaction are added to obtain the total overall change in the enthalpy in the one big equation. All right, so here's an example problem. We basically have 2C plus H2, and then that yields C2H2. And that's the equation that you want to find with the 3 given thermochemical equations. So I'm not going to read them out, but you can just take a look at it as I go over the problem. So you basically flip reaction 1 to get C2H2 on the product side, and you flip the sign on the enthalpy, because then you can cancel them out, and then that would just give you 2CO2 plus H2O yields C2H2 plus 5/2 O2. And then this will give you, since you have to flip the sign on the enthalpy, this will just give you 1,299.5 kilojoules. Okay, and then now that you have that, you basically can see at the bottom of the screen right there. Now you just want to multiply reaction 2 to get 2 solid carbon atoms, so then you can cross them out. If you have to multiply the reaction, you also have to multiply the enthalpy by 2 as well. Okay, and now you can see in about the top left-ish part of the screen, you can see the reaction that we now have. So as you can see, you have the 2 CO2 on one side and the 2 CO2 on the other side for the second and the first equations. We have the 5/2 O2 on the first equation on the right, and then we have the 2 O2 on the left of the second equation and the third equation. So then those can cancel out, and the CO2s can also cancel out. The H2Os can also cancel out because you have it on the left side of the first equation and on the right side of the third equation. So after they all cancel out, you will basically get the equation that was you originally wanted to find, which was 2C plus H2 will yield C2H2. And now you basically just want to add all of your delta H's together, and that will give you 226.7 kilojoules. I love Hess's law too. Hess's law is great. All right, so now we're going to do a little quiz to go over everything in this unit. I believe we're going to have a link soon. All right, we do have a link. Okay, I'm going to drop the link in the chat. I don't know if that's the right link. Please let me know if that's not the right link.
They can scan the QR code on the screen right there.
Okay. Okay, so that's not the right link. My bad. There's the link right on the screen, and that's the right link. Sorry, guys. Yeah, and whoever gets the link, please send it. Okay, yeah. I think someone just posted on the chat. The QR code is correct. Yes. Thank you for posting in the chat. All right, so I think we'll just wait for a few more people to join, and then we'll start the quiz. So someone asked, so in Hess's law, you add all the delta H's once the equations cancel out. That is true. That is what you do. You just want the equation that they give you. You want to basically get that through canceling out different things and manipulating the equation.
All right, so it looks like we have a good amount of people that are participants. So let's just start the quiz.
Okay. Oh,
We turn off the music.
Okay, so this says, then what does the positive sign on energy mean? Energy flowed out of the system, work was done by the system lost thermal energy, and system gained thermal energy.
Looks like some people did actually like the music. All right, we're getting close to the answer. I'm gonna review it real quick. There we go.
Oh, yes. Yay! Most of you guys got that right. The positive sign on energy basically means that the system gained thermal energy, and that is related to endothermic processes, which the heat travels from the surroundings into the system. That's your endothermic. All right. Good job.
Next question.
You guys got this. All right. So next one says, if a 55-gram metal at 35 degrees Celsius is added to 50 grams of water at 20 degrees Celsius, and the resulting mixture is heated to 30 degrees Celsius, what's the heat capacity of the unknown metal? All right, guys, you got this. For this one, you can use your calculator.
Yeah, a lot of people are saying we need Q, but just to give you guys a little tiny bit of a hint, you want to make Q equal Q. So you're basically going to have MCAT equal MCAT.
Mm-hmm.
That's all right. If you guys are confused, we're going to go over this question. So
Okay, I think we can reveal the answer now. We have a lot of
yeah,
responses.
let's do that.
Okay, so I see a lot of mixed answers. So the actual answer is 8.8 joules per grams of Celsius. And basically what you have to do for this problem is you have to set Q equals MCAT equal to Q equals MCAT. Since there's two different Q equals MCATs, you want to set them equal to each other, so MCAT equals MCAT. You want to find the heat capacity to C for the unknown metal. So you want to basically plug in all the numbers into the equation. You get the heat capacity of water from a specific a sheet that they'll give you, so you don't need to actually know this from the top of your head. So after you plug in all the numbers into the equation and then you solve for C, you will get the heat capacity of the unknown metal.
Yep. All right, next question.
All right, so the enthalpy change of a reaction is usually measured at either a constant temperature, a constant pressure, a constant entropy, or a constant volume.
Don't worry, guys. After the quiz, we're going to go over question 2 because we've been getting a lot of questions on that, and I can show you step by step on how to solve that one.
All right, I think we can reveal the answer now. We have a bunch of people. Okay, so the enthalpy change of a reaction is typically measured at the constant pressure. This is just something you need to know for the AP exam.
All right, so that concludes our quiz. Because of time, I'll try to talk about question 2 at the end of the whole lesson, because we want to get through the girthy part of the whole unit 6 to unit 9, especially unit 8. So let me change the sharing. All right, so now let's talk about Unit 7, and Unit 7 is 7.7 to 9% of the exam. Let's get started. Now, we want to start by talking about the introduction to equilibrium. We want to know what equilibrium is. And every time I think of equilibrium, I think of my science class where my teacher got a hairdryer and had a ping pong ball and let the hairdryer go on, and the ping pong ball would stay in a stationary position while still rotating. And that's when it was in equilibrium. But in AP Chemistry, equilibrium is when we identify our reversible reactions, and our reversible reaction is just when chemical reactions can occur in both directions. So you can see that we have this formula over here. So we have A plus B, and it can go in both directions, and our products are C plus D. And in equilibrium is reached when the rate of the forward reaction is the same as the rate of the reverse reaction. Now, when I think of equilibrium, besides the ping pong ball example, I always think about kind of like a seesaw, but I don't have a seesaw laying around here, so I'm just going to demonstrate that with a pen. So let's say our reactants are on this side and our products are on this side. And in equilibrium, we are in a state in which we're keeping the reactants and the products pretty much the same. We're keeping the rate at which they react the same. And this is also in dynamic equilibria, in which the reactants and products are continuously reacting, which is moving this way and that way. Now, let's move on to concentration versus time graph, what equilibrium would actually look like. And you should be familiar with this graph. It's when the reactants dip down because the reactants are obviously decreasing and the products are increasing, since we're moving to the forward rate, going from reactants to products. And when the concentration of the products is at a stagnant place and it's parallel to the reactants, that's when we've hit equilibrium. Now let's talk about forward and reverse reactions. And this is when the rate of the forward reaction and the rate of reverse reaction, which we stated, was equilibrium. Now, when the forward rate of the reaction is higher than the reverse, more products are formed. And when the reverse rate of the reaction is higher than the forward, more reactants are formed. So if we look back at the pen example, we can see that when we have a higher forward rate of reaction, we have more of our reactants. So it's going to move up kind of like this. We have more reactants. So to balance that out, our system creates more products. And when we have a reverse reaction rate, this is higher than the forward. So more reactants are produced. So when we're basically over here, more reactants are produced because we're going from a reverse rate of reaction. So we're making more reactants. Now let's talk about reaction quotient and the equilibrium constant. Now, equilibrium constant is usually denoted by K, and this is the relative concentration of a reaction species at equilibrium. Now, this is important because this is at equilibrium, and the reaction quotient is the relative concentration of the reaction at any time. It doesn't necessarily have to be in equilibrium. And to denote the equilibrium constant and the reaction quotient for solutions, it's usually there's a C on the bottom, and for gases there's a P. And this formula sheet to hopefully that's my right over there, but that's going to be on your AP Chemistry formula sheet. So if there's going to be some FRQ questions, maybe it's going to be the first one that says create or state the equilibrium constant, and you can look at the AP Chemistry formula sheet and boom, you can already get that easy point. Now, when the equilibrium constant is greater than our reaction quotient, then we have the forward reaction being favored until the equilibrium is reached. And the whole reason why we have the reaction quotient is so that we can see if the forward reaction is more favored or the reverse reaction is favored. So then we can see if more products are being formed or more reactants are being formed. And if the reaction quotient is equal to the equilibrium constant, we are at equilibrium. And if the reaction quotient is bigger than the equilibrium constant, then where the reverse reaction is favored until equilibrium is reached. So just think about it like this. If the equilibrium constant is bigger than our reaction quotient, then we're producing more products. And if our reaction quotient is bigger than our equilibrium constant, we're producing more reactants. So if Q is favored, more reactants. If K is favored, more products. So that's pretty simple explanation for that. And K is usually products over reactants. So if we have more of K, if K is a number like 16, the only way it became 16 is so that our products, which is our numerator, is a bigger number than our denominator. And for our Q, this is basically reactants over products, so it's vice versa. So we're going to have more, if a Q is bigger than K, we have more reactants over the products. Now, so we move on to the magnitude of the equilibrium constant. And this is a very important graph that you must know for the AP Chemistry exam, and it's when our K value, basically representing our K value, which is less than 0.001, and this means that the reaction barely proceeds, because if we have a higher K, that means the reaction will go to completion. That means it'll be more favorable to go to completion. Now, if our K is less than 1, then our reactants are favored, and it's not like smaller than 0.001. It's basically that it's smaller than 1, and if our products are favored, that's when K is greater than 1. And if K is like abnormally greater than 1, maybe like, I don't know, 50 or even 100, then our reaction goes to full completion. So now let's talk about the properties of the equilibrium constant, and I kind of think of this as Hess's law, but it's not, because Hess's law is usually entropy or enthalpy. So it's kind of the same rules that apply, but they're kind of different. So I always think of Hess's law as solving a puzzle, and this is basically solving a puzzle. So when you're trying to create the bottom reaction from those two reactions that you're given, if you want to flip the reaction, you must make K inverse. Now, in Hess's law, when you flip the reaction, you just change the sign. If it was negative, then it's positive now. But since we're flipping the reaction for our equilibrium constant, it's going to be 1 over K. Now, if we're multiplying the reaction by a factor, we have to put that number as a subscript. Now, in Hess's law, when we were multiplying it by a factor by 2, we just multiplied our enthalpy by 2. But for the equilibrium constant, we have to square that number or cube it, or whatever the number is. We have to put it in a subscript. And if you're combining two reactions, you must multiply the K values. Now, in Hess's law, we added the enthalpies. We added the end enthalpies. But for the equilibrium constant, you have to multiply all those K values. So you can see how they differ, but it's still kind of like solving a puzzle. Let's do some practice on the equilibrium constant, and just to show you how it's different from the rules that we learned from Hess's law. Now, since I consider a reaction of N2, this 3 moles of H2, and then we're in equilibrium, so that goes to 2NH3, and that has a K value of 0.118, and then asks us to find the equilibrium constant for the reaction that it looks like it's flipped. Now, when we talked about our past rules, we said that if our reaction is flipped for the equilibrium constant, this is 1 over our equilibrium constant. This is the inverse of the equilibrium constant that we've been given. And the inverse of that is 1 over 0.118. And this will be 8.47 as our new equilibrium constant. So remember, our final K when we're flipping the reaction is going to be 1 over our initial K. So let's try to calculate the equilibrium concentrations, and it's your favorite graph. It is the ice chart, is the ice tables. That's your favorite table. I'm sure it is. It's one of my favorite tables, and I love the ice table because it's just so simple to answer a bunch of questions. So let's look at this question. If the initial concentration of A and B are 2 moles, what is the equilibrium constant if the equilibrium concentration of AB is 1.55 moles? Okay, so we're obviously given the moles of the concentration of A and B, so we just put it up as our initial. And since we stated that the equilibrium concentration of AB was 1.55, for the concentration, we put that under equilibrium. So we know that usually when you're given the equilibrium concentration and the other reactants are your initial, you know that that's going to be your change. And what you do on the product side, you do the inverse on the reactant side. So since we added 1.55 moles for our concentration of AB, we need to subtract it from 2 moles, and then we get 0.85 for A and B, and for AB we get 1.15. So you can think of this as if we're given the number initially, usually we're going to subtract it, but it's always the inverse. When we have our products that are added, like as we can see from AB, our change is adding 1.15 moles. Then on the reactant side, we're subtracting that 1.15 moles. And when you put that in your equilibrium concentration, when you set up your equilibrium concentration, which is obviously going to be products over reactants, like we talked about, it's going to be 1.15 over 0.85 squared, or 0.85 times 0.85, and that'll get you 1.592. Now let's look at another question, and it asks us to suppose the initial concentration of CO2 and F2 at 4 moles, and what is the equilibrium concentration of 2ClF if K is 16? Now, as we can see, K is a pretty big number, so we're obviously going to know that it's going to be more products or reactants, so more products are going to be favored, but that's just some background information that you could know. So we know our initial concentration is 4 moles for our Cl2 and 4 moles for our F2, and we're not giving the initial concentration of 2ClF, but we're not even given the equilibrium concentration at all. So from here, you use your x. You use your variables, your unknown variables. So it's going to be 4 minus x on the reactant side, 4 minus x on the reactant side as well, and we're going to have plus 2x. Now, the reason why we have a plus 2x instead of just plus x is because we have 2 moles of ClF, and when you have that coefficient, you're gonna have to account for that in the x part. So we always have plus 2 and 2x, and we square that because we're still in because our coefficient is still there, the 2ClF. So it's kind of, sometimes you can forget this, but you have to remember that when you're setting the ice tables and you have the coefficient given, you need to account for that in the x, and you need to put it as a subscript. And when we divide that over our reactants and make it equal 16, we can put it on our calculator, and our calculator can solve it. And when our calculator solves it, we will get, for x is 2.667. And since the question asks the equilibrium concentration of 2ClF, we know that the equilibrium concentration is 2x. So that's 2 times 2.667, and that'll get you 5.33. And if you guys have any questions about Unit 7 at all, you can leave it at the Q&A. We'll talk about that at the end of the presentation. So now we've been dealing with ice boxes, but let's just talk about it in a little more detail. And when we're doing ice boxes, we may find something like this, in which we have x squared over 4 minus x. And sometimes we can use approximation in that 4 minus x is x, because remember, if we have and this is only if we have a small k, if we have a small equilibrium constant that we can approximate, and x is going to be super tiny, which means that the 4 minus x is pretty close to 4, and that basically is 4. So this is only, remember, this is only if we have a very small equilibrium constant that we can make these approximations, and this just helps our math go by faster. Now let's look at a representation of equilibrium. And this is just a sort of what the moles would look like in a, I guess you could say, a jar or a square. And we have A plus B, and that goes AB, and we're in equilibrium. So the initial equilibrium, we have 3 moles of A, 3 moles of B, and 1 mole of AB. And I apologize, I didn't color code this part. But we know that the amount of moles of A and the amount of moles of B are the same. Now, if we add AB, then we get 2 moles of AB, and then we have 3 moles of A and 3 moles of B, and we keep that the same. So we're maintaining our equilibrium. Because if we add that AB, our reaction, our system will counterbalance that and try to stay in equilibrium. So we still contain our 3 moles of AB, 3 moles of B, and 2 moles of AB. So what does it look like on a graph? Well, let's look at the concentration of A, and you're usually going to have to understand these graphs. So we have our initial equilibrium, and when the time the AB was added, we have a new equilibrium that increases. Now, I believe the other chart didn't show that increase, so we want to look at these graphs. I apologize since the diagrams didn't really show that, but we increase our equilibrium. And for B, we also equally increase our equilibrium. Since we're adding more products, we need to increase the amount of reactants so we can keep that dynamic equilibria. And we have a higher new equilibrium. And for AB, when we add AB, we have a less of an equilibrium. So when you're adding the, for example, we're adding the product, it's going to have a dip. We're going to have a smaller equilibrium when it goes down. And this is basically a chart that this is a graph that'll show you the representations of equilibrium. Now it's time for a brain break. I did bombard you guys with a lot of Unit 7 stuff, so it's time for you to take a break, get some water, and we'll be back soon. All right, so brain break is over. Let's keep on going. So now let's talk about Le Chatelier's principle, which is basically applying temperature, pressure, and volume and relating that to equilibrium. And it's a system at equilibrium will stay at equilibrium until a stress is applied, which is temperature, pressure, and volume. Now, temperature will only change the value of K, and any change in concentration or pressure will not change K, but it will change the amount of concentration of either reactants and products. And if the concentration of products are increased, the reverse reaction will be favored. Now, like we said, the system will counterbalance the change to return to equilibria because we are in dynamic equilibria. And this change can be in a concentration, temperature, volume, or pressure. And let's talk about some of the changes. So if there's a change in concentration, there's a changing of Q. And if the temperature, changes in temperature depend on the reaction, if it's exothermic or endothermic. An increase in pressure leads to a shift to the side with fewer moles of gas. So let's kind of break this down. So let's just say we added more volume, right? If we increase the amount of volume, whichever side on the products or the reactant side that has the most moles is going to be favored. So if we look on the chart under the definitions, we have A plus 2B, and then there's C plus D. Now, when we increase volume, the side with the most moles is going to be favored, so the reactant side is going to be favored. Now, if pressure is increased, that means we have a decrease in volume. And if we have a decrease in volume, the side with the least amount of moles will be favored. So our product side will be favored. So when we're talking about pressure, we want to relate it back to volume. And volume is going to pretty much be equal to moles. So they're going to have a direct relationship. So if volume increases, whichever side has the most moles will be favored. And if volume decreases, whichever side with the least moles is favored. And we relate that to pressure. Now, if we're talking about temperature, it depends on where our heat is placed. And also if the reaction is exothermic or endothermic. So let's just say our reaction is exothermic, right? If our reaction is exothermic, and here's my little mouse over here, then our heat is going to be here. So we're going to have plus heat on the product side. And if we increase the amount of temperature, the side with the least temperature is going to be favored. So it's kind of like a fire, right? We're obviously, if a building is burning, we're obviously going to run away from that place because it's a burning building. So when we have plus heat over here, we're going to run away to the reactant side. And if we have less heat, our products will be favored if we're in exothermic. If our heat is here and we have less temperature, if temperature is taken out or we're in cooling, then the product side is going to be favored because our reactants are going to be converted to products. And you can think of it as we want warmth, so we're going to go to the heat. Now, I pretty much covered most of this when I was talking about the discussion with the moles, and you could look at this just as reference. And one of the things I really want to highlight is that adding a catalyst does not add stress to the system. And this does not change, this does not favor the reactants, this does not favor the products. So catalysts, you could pretty much say that catalysts don't do anything as a basic understanding. You could just say that catalysts don't do anything. And I mean, they do something, but they don't add as much stress to the system that it'll affect the concentrations. And let's look at the introduction to solubility equilibria. And this represents the equilibrium constant with KSP. And the SP stands for solubility. So anytime a question asks you about KSP, it's talking about solubility. And when you're finding your KSP, you can forget about the reactants because it's obviously going to be a solid and you only account for the products. And a higher KSP means that more of the solid will be dissolved, and a lower KSP means that less of the solid will be dissolved. So you can think about it relating back to equilibrium constant, in which if we have a high equilibrium constant, we're forming more reactants, and if we have a very low equilibrium constant, we're almost forming reactants. Higher KSP means forming more products. And as you can see, like I stated, the KSP will be our product. So that's going to be sodium times chlorine. Let's look at the common ion effect. And we're going to look at that through our ice tables. Now, like we stated, since sodium, our table salt, is a solid, we can forget about that because it's a solid. And we only have to focus on the ice tables for sodium and chlorine. So the question asks, suppose the initial concentration of chlorine in aqueous form is 0.2 moles and the KSP is 3.14 times 10 squared. What is the equilibrium constant of the sodium in aqueous form? And we're not given the initial concentration of sodium. We're given the initial concentration of chlorine. So we add the X to the sodium side because we have 0. You can't really subtract X from that. It's usually when we don't have the initial concentration, we want to add it. We want to add an X, so that'll be X for sodium, and 0.2 plus X will also be X. So you're basically just adding your X's. There's no subtracting X's from here. And when we solve that, we're going to get 0.2 plus X times X equals 3.14 times 10 squared. And if you solve that, you're going to get 17.62 as your X. And that is your concentration for sodium. Now let's look at pH and solubility. And Dylan will talk about pH and acids and bases in more depth. And this is just the introduction, just to get you warmed up into Unit 8. And here's a representation. Here's just a reaction showing a base acid, a conjugate acid, and conjugate base. And if we increase the pH, we're adding more hydrogen ions. I mean, go figure. If we're increasing pH, pH is basically dependent on the hydrogen ions. And if we turn OH to H2O, this results in less OH, which means that we have less products. And to counter this, the system produces more NH4. So as you can see, if we increase the pH, we're increasing the hydrogen ions. Hydrogen will bind to the hydroxide, forming water, and we have less products. So to counterbalance that, we need to produce more products. We need to produce more of our conjugate acid. And this is also going to warm me up to Unit 8, which Shreyas will talk about. And this is a free energy dissolution. And it talks about enthalpy and entropy, which are responsible for the ability of reaction to take place. So for enthalpy, an exothermic reaction is more favorable, or if our enthalpy is negative. And for entropy, it's just a measure of disorder or randomness, and more entropy is favored. So for a thermodynamically favorable reaction, our enthalpy must be, or preferably should be, negative, and our entropy should be positive. And this is just Gibbs free energy, and it's only will occur if it's negative. So we will only be thermodynamically favorable if our delta G is negative. So you're going to have to remember this chart, memorize it before the exam. And it's when we have our exothermic reaction, or our delta H is negative and our delta S is positive, and this will always occur. This is always thermodynamically favorable, no matter what. Now, if we look on the flip side, when we have an endothermic reaction, or when our delta H is positive, then this will only occur in high temperatures, and our delta S is negative. This will only occur in high temperatures, because when we're looking at our equation, that delta G equals delta H minus T, and then we have delta S. We need it to be more negative, so we're going to have more temperature. And you can look at the graphs. You can continue looking at the graphs. And now remember this: when we have the endothermic reaction, when we have an endothermic reaction and we have our entropy being negative, this will never occur. This is never thermodynamically favorable. All right, so now it is quiz time. This is the best part of the entire lesson. At least I think it's the best part, because we get to test out our knowledge. So let me share that real quick. All right, there we go. There's your QR code, and we're gonna get started soon. All right, so let's get started. Oh, let me turn off the music. All right, so what is the purpose of calculating the reaction quotient in a chemical reaction? Now, we're going to answer this question. We're going to try to answer it in a minute, or even under a minute, because we want to prepare you for the actual exam, and you're going to get about 1.5 minutes or a minute 30 seconds. So try to answer as best as you can, and we'll reveal the answer soon. All right, so let us reveal the answer. Okay, so 85% of you got it. So it is A, to predict the reaction to predict the direction of the reaction at the given time. And we discussed this before. The reaction quotient is just to help us to compare the equilibrium constants so we know which direction is being favored. All right, so let's look at the next question. This is a little bit of a longer question. I think you're going to have to solve it with the calculator, but we have the reaction of A equilibrium at B plus 2C is also going to start with 0.8 moles of A in the concentration of 1 liter. The reaction occurs, it is found that there are only 0.2 moles of A left once equilibrium is reached. Which of the following shows the concentration of C at equilibrium? Exactly, it is ice table time. All right, so unfortunately, a minute has already passed, and you guys will get more time in the AP Chemistry exam, but we want to condition you to answer it faster, so let's reveal the answer. And the answer was 1.1 moles, and I'll try to explain it in the Q&A. So remind me to talk about this question in the Q&A. You could drop it in the Q&A box to talk about question 2, but because of time, we want to move to Unit 3, because Unit 3 is obviously the best unit. All right, so now let's look at question 3, and it says for the reaction, what would the expression look like to solve for the concentration of C at equilibrium? And obviously, we have to remember our K are equilibrium constants. So try to solve this question as best as you can. You got a minute. All right, so a minute has passed, so let's reveal the answer. Oh, and looks like we were split on this one, but the answer was D. And when we we can start by creating our equilibrium constant, which will be C squared times D over B squared times A. And then we have to isolate for C, so that's basic algebra. And we'll look back at that in the Q&A. But that wraps up our quiz for Unit 7. And don't worry, we will look back at the answers, especially we'll look back at Unit 6, the Unit 6 quiz. But now let's move on to our next unit, which Dylan is going to be the goat at it. It's Unit 8, baby. And I love Unit 8. So I'm going to listen to this one too, because I'm taking the AP Chem exam as well. So let's get started. And Dylan, I'll let you take it away.
All right. Thank you so much. Okay. So I know we're all very scared about Unit 8. It is the scary unit. It is that unit that makes every student shake in their boots. But actually, I'm going to start this off by saying Unit 8 is not as bad as you think when you remember. It is almost entirely an extension of Unit 7. So if you can do plain old equilibrium, you can actually handle acids and bases pretty okay. There's some nuances there. It's definitely not an easy unit, but you can handle it. So I'm just going to start it with that. So if you're scared, valid, but we got this. All right, so let's get started. So the first thing we need to understand when talking about Unit 8 is just what an acid and a base is, right? Because we might have talked about them before, but we really have to get a solid definition of them if we want to properly understand how to deal with acids and bases. So there are two main definitions of acids and bases that we talk about on the AP exam, and that is the Arrhenius definition and the Bronsted-Lowry definition. They're very similar, but there's a slight nuance in the Bronsted-Lowry definition that differentiates it. The Arrhenius definition is what we think about when we think about like our traditional acid, our hydrochloric acid, our acetic acid, our hydrofluoric acid. And that is a substance that releases H plus into solution, or a base releases OH minus. So for example, NaOH or CaOH or any of those solutions. They are Arrhenius acids and bases. A Bronsted-Lowry base or acid thinks of it more as a donation of a proton. So for example, HCl will react with water to create what's called a hydronium ion and chloride, right? So in this case, instead of hydrochloric acid releasing H plus into solution, it donates that H plus to, in this case, the base, water. And we'll talk a little about how water can function as both an acid and a base. Similarly, we look at ammonia, something that actually doesn't release OH into solution. It is not an Arrhenius base. However, it's a Bronsted base because when we react it with water, right, water will act as an acid and donate a proton to ammonia, creating ammonium and hydroxide ion, creating a basic solution. So that's our basic definition of an acid and base. And something you should be keeping in mind whenever you're looking at these is not necessarily which definition are we using, but thinking about the fact that when we're looking at acids and bases, there are multiple ways to interpret them, in that we can look at donating hydrogen ions as a way of expanding the field of basic solutions and acidic solutions. So let's get into it. So what we want to talk about next is what happens when an acid or a base actually dissociates, right? Because it doesn't just release H plus or OH minus into solution, but it leaves behind some other things. So for example, when hydrochloric acid dissociates in water, it donates its proton to water, creating a hydronium ion, and leaves behind a chloride ion. When you take that hydrogen off of chlorine, right, you create something that's hungry for protons, right? You've broken up that stable pairing. You have something that will theoretically take a hydrogen ion and recreate itself. So we can think of the chloride ion as actually a base. We'll talk about why it's actually an incredibly weak one. However, it's a base, right? We call it the conjugate base of hydrochloric acid because it's derived from that. Likewise, we can call hydrochloric acid the conjugate acid of the chloride ion. This becomes a bit more clear when we look at a weak base or weak acid that actually creates a conjugate that has some significant features. So when we look at the reaction of ammonia and water to create ammonium and hydroxide, ammonia is something that wants to give away its excess H plus ion and re-become ammonia. So it's going to act as an acid, right? It is the conjugate acid of ammonia, and vice versa. Ammonia is the conjugate base of ammonium. So in this case, what will happen in the reverse reaction is ammonium will donate its H plus ion to hydroxide to create water and ammonia. So both of those reactions are happening at once. Ammonia is acting as base, ammonium is acting as an acid. So when we're talking about the strength of conjugate acids and bases, something we need to note is that the conjugate acid and or base of a strong base or acid is insignificant. So for example, the chloride ion is an insignificant base. And what we mean by that is that it will not contribute to pH or POH. That's because HCl is a compound that is such a strong acid, it wants to get rid of its hydrogen. It's just going to throw those hydrogens out there and pretty much fully dissociate. That reaction basically goes fully forward. So there isn't that much Cl minus in there, and therefore it is not a significant base. However, when we have something like ammonium, which actively has a significant concentration in the solution, it's a significant acid because NH3 is a weak base. And we'll do some math to understand why that actually is a bit later and do more quantitative work on that. So we've talked a little bit about how water can act as both an acid and a base, right? It's a little confusing, but it's because water can dissociate into an H plus and an OH, meaning it can both donate hydrogen and release hydroxide. So let's take a look at an equation that is a pretty important one, and it's called the autoionization of water. And what the autoionization of water tells us is that water ionizes itself. It can donate a proton to itself to leave an OH minus along and create a hydronium, right? And that tells us that two waters react and auto-ionize. So that's why it's called the autoionization of water, right? So in this reaction, one of the waters is acting as an acid, releasing a hydrogen ion, and the other one is acting as a base, accepting that hydrogen ion. And something that's really important to note is this equation has a K value, right? It runs in equilibrium, and it reaches a point where the creation of OH and H3O is equal to the creation, the rate is equal to the rate of creation of water. So in this case, the K value is a special constant called Kw, and it's equal to 10 to the minus 14. And we'll see why that constant is actually really important. But for now, just note that that is the equilibrium constant of that equation right there, of two waters reacting to form a hydroxide and a hydronium ion. So this will all kind of come to a T when we can finally look at pH, right? So pH is a measure of acidity. I'm sure most of us, if not all of us, are familiar with that, right? We talk about the pH of acids and the pH of bases. And generally, the notation we're seeing here is that the P of something is actually just the negative log of that something. So pH is the negative log of the hydrogen plus concentration. POH is the negative concentration of the hydroxide concentration. So let's do a little bit of math and see what happens when we add pH and POH together. Well, we have our two logs are added. We can use logarithm properties to multiply the H plus and OH minus. That's just a property of logs that you might have learned in math class, and bring out the negative. And note, H plus, or typically H plus can be kind of swapped out for H3O plus. So we can think of that as hydronium and hydroxide. Well, that was the equilibrium constant for autoionization of water. So that's just Kw, which is 10 to the minus 14. We plug that into our negative log, and we find that pH plus POH equals 14, which is a pretty key equation that we'll be using on the exam, which means if we know either the concentration of H plus or OH minus, we can find the other, simply because we know, if we know the pH, we know POH. If we know POH, we know pH. Another thing to note is that the pH scale is logarithmic, which means a change in pH, like a change in one pH value, isn't an increase or decrease in a constant number. It's multiplicative, which means a change in 1 is 10 times more or less hydrogen concentration. A change in 2 is 100 times, 1,000 times. It's not 1 times, 2 times, 3 times. Just something to kind of keep in mind as you look at that. Because a change, a difference between 7 and 1 can seem kind of small until you remember that is a 10 million times greater concentration of H+. Okay, so talking about strong acids and bases. Strong acids and bases completely dissociate in water. That means that when we put it in water, that reaction goes fully forwards. So, for example, hydrochloric acid is our classic strong acid, right? When we put that in water, that'll just go fully forwards, right? It'll pretty much all those hydrochloric acid molecules will have split into H plus and usually form hydronium, and Cl minus, the conjugate base. And we'll talk about weak acids and why that doesn't happen with them. The examples of strong bases are typically group 1 and 2 hydroxides. So sodium hydroxide, calcium hydroxide, anything from those groups. So potassium hydroxide, magnesium hydroxide, typically all of those are strong bases. Strong acids, there are 7 strong acids that you need to know. And typically these just have to be rawly memorized. There really is no rhyme or reason. You can typically think about the molecular structure of them and understand, like, well, chlorine's got a very high electronegativity, bromine does, iodine does. But typically, these just have to be rawly memorized. And through use, you will get them. And they are hydrochloric acid, nitric acid, sulfuric acid, hydrobromic acid, chloric acid, hydroiodic acid, and perchloric acid. And again, they just kind of have to be memorized. But note that when you put any of these acids into water, they go fully forward. They will fully dissociate in water. I want to make a note on sulfuric acid, though, because sulfuric acid is what we call a polyprotic acid, or a diprotic acid in this case, because 2 hydrogens, right? It's got 2 protons. Both of those hydrogens will come off. Only the first hydrogen does so in a strong sense. So all of those first hydrogens will fly off. The second hydrogen, HSO4 minus, or hydrogen sulfate, will be a weak acid, right? So that's something important to note, that H2SO4, when dissolved in water, will only release 1 hydrogen when we're talking about the strong base. If we're talking about hydrogen sulfate, that's a different story. But sulfuric acid will only release that 1 fully. Okay, so let's take a look at an example, right? Let's take a look at the pH of a hydrochloric acid solution. And the problem is pretty straightforward. It is, what is the pH of a 0.5 molar solution of hydrochloric acid? Well, we know that hydrochloric acid in water will dissociate into H plus and Cl minus. And we could write this as HCl plus H2O yields H3O plus and Cl minus. This is just kind of simplified. We know this reaction will go fully forward. So every 1 mole of HCl will be transformed into 1 mole of H plus, which means our concentration of hydrogen is equal to our initial concentration of HCl, which is 0.5. Now, using our formula for pH, we know that pH is the negative log of H plus, which is the negative log of 0.5. Plug that into a calculator. You can't do that by hand. And you get a pH of 0.3. These problems are typically the most straightforward pH problems you'll see. And again, you can just think of this almost like stoichiometry. It is a straightforward chemical equation. There is no equilibrium happening here. This is just 0.5 molar HCl turning into 0.5 molar H plus and 0.5 molar Cl minus, and finding the pH from that concentration. Similarly, we can look at the pH of a basic solution, in this case, sodium hydroxide. In this case, the question is asking, what is the pH of a 1 molar solution of sodium hydroxide? Once again, sodium hydroxide will fully dissociate in water into sodium plus and OH minus. So that 1 molar NaOH is going to turn into 1 molar Na plus and 1 molar OH minus, and therefore our OH concentration is 1 molar. So you might think, okay, perfect, take the negative log, and we're good, right? We're perfect. However, remember that this is the OH concentration, and we're looking for pH. So first we need to calculate pOH and use pH plus pOH equals 14. So in this case, we can find the pOH by doing the negative log of 1, which is 0. So pH is 14 minus pOH, just rearranging that equation. And boom, we get a pH of 14, not 0. That's an important kind of mistake that a lot of students will make, is they will find pOH instead of pH. And depending on what the question is asking for, you might get that wrong. So just be careful when you're looking at basic solutions in particular, because I think we tend to default to pH. Okay, now let's get into kind of the meat of unit 8, right? And that is weak acid and weak base equilibria. In particular, the key point here is that weak acids and weak bases incompletely dissociate. That means that they will dissociate, but then that reverse reaction will also occur. Where, for example, HA, which is a generic acid, right? We don't know what A is, but it's some conjugate base. HA, right? HA will split up and form H3O plus, will react with water, and A minus, the conjugate base. Since HA is weak, that reverse reaction will also happen, where A minus will take that H off the H3O plus and reform HA. So we've got an equilibrium. We've got the rate of H3O and A minus creation and the rate of HA creation. And from that, we can plug that into the law of mass action and form an equilibrium constant that we label as the Ka. I want to note the Ka is just an equilibrium constant. It is the same as every other K you've seen in this class. We just note it because it is a special reaction, which is the dissociation of a weak acid. And that's the formula there. But again, it's just an equilibrium constant. So if you know how to do equilibrium, you can find the equation for Ka. Similarly, if we have a weak base, we have that base reacting with water to create BH plus, the conjugate acid, and OH minus. But because it's a weak base in this case, it will incompletely dissociate, and we will have that reverse reaction kick in as well. And when those two rates are equal, we'll have an equilibrium. Once again, Kb is just the equilibrium constant for that reaction. Almost always, Ka and Kb are given, right? They're constants that are determined mathematically and experimentally. However, they can be calculated if you are given the Kb of the conjugate base or Ka of the conjugate acid. And that's because, and this is a really cool equation, I think it's really cool. Ka times Kb for a conjugate acid-base pair is equal to Kw, right? And this can be derived pretty easily algebraically. Give it a try. Not required for the test, which is why I'm not going to do it, but you can do it. And it's a pretty simple derivation. And this is actually why the conjugate acid or base of a strong base or acid is negligible, because when the Ka of the dissociation of HCl is super high, the Kb for the formation of, or for the reaction of Cl minus has to necessarily be really small, right? And you can try that out. If you look up the Ka of HCl, you can find that it's really high. So plug it into Ka, Kb equals Kw, and you can find that the Kb of chloride is like 10 to the minus 21 or something. It's like non-existent. So that's something that's also important to note. And we'll look at applying Ka and Kb in further slides and look at problems involving them. Perfect, great. Here we go. So here's a problem that asks us to find the Kb of acetate, right? So we're told that the Ka for the dissociation of acetic acid, CH3COOH, is 1.8 times 10 to the minus 5. And we're asked for the Kb of the conjugate base, CH3COO minus, or acetate, right? And we know that acetate is the conjugate base of acetic acid because if we write out the dissociation, we can see that CH3COOH will react to form acetate, the conjugate base, NH3O plus. So if we know the Ka of acetic acid, we can find the Kb of acetate. So you know Ka is 1.8 times 10 to the minus 5. That was given. Solve for Kb using the formula, plug in the numbers, and you get 5.56 times 10 to the minus 10. It's a pretty cut and dry problem. However, you may have to use this technique to do more steps. For example, if I'm told to find the pH of a solution of sodium acetate, but I'm only given the Ka of acetic acid, my first step would be finding the Kb of acetate, because then I could use the Kb expression for acetate. Excuse me, I can use the Kb expression for acetate to then calculate that pH, because I can then write out the equation of acetate reacting with water to form acetic acid and OH minus, right? Find the concentration of OH minus from there, and boom, we've got a pH. Well, we've got a POH, and then we can find the pH. Similarly, here's what we were just talking about, right? Find the Kb of chloride, and I'm going to move through this problem relatively quickly, right? We're told that the Ka value for the dissociation of HCl is 1.3 times 10 to the 6th. First of all, note that that's disgustingly high, right? HCl is a strong acid. So what's the Kb of the conjugate base, HCl minus, or Cl minus, excuse me. So we can write out our dissociation and use Ka, Kb equals Kw, and we find a Kb of 7.6 times 10 to the minus 21, right? So this kind of shows how Ka, Kb equals Kw can give us a reasoning as to why the stronger an acid or base is, the weaker the conjugate. Okay, actually, let's skip this slide. This was a problem we were all playing with and we were having trouble with, so I won't explain it. And it's not really relevant to the exam. It was just to show how weak of a base Cl minus was. Okay, so now let's look at actually applying these things. So we know that the Ka of acetic acid is 1.8 times 10 to the minus 5, and we are asked to find the pH of a 6 molar solution. This is just an equilibrium problem, right? Break out those ice tables, drop the ice table hype in the chat. Exact same process. We start with 6 moles of acetic acid and 0 of the products. We lose X of acetic acid and gain X of our products. We get 6 minus X moles of acetic acid and X moles of H plus and CH3COO minus. We can plug that into our equation. Assume X is very small because look at that Ka. It's not going to go, this reaction is not going to go very far, right? So we can say that X squared over 6 is 1.8 times 10 to the minus 5. We solve for X, and we find that this has a pH of 2. Likewise, we can find the pH of a 3 molar solution of ammonia, which has a Kb of 1.8 times 10 to the minus 5. I want to note that the fact that the Ka of acetic acid and the Kb of ammonia are the same is raw coincidence. I think it's really cool, but it's raw coincidence. So don't think there's a relationship there. Like before, we can just treat this like an equilibrium equation, right? Water is omitted because we don't include liquids or solvents. But we know we have 3 molar NH3 and 0 ammonia and 0 OH minus. We lose X of our reactants, gain X of our products, and we go through the equilibrium process to find the concentration of OH minus. Then we can find the POH, then we can find the pH. That's generally how these problems go. You find a concentration, plug it into the negative log, maybe do some more math, and you get a number. But I want to really emphasize that this is all just equilibrium. If you can do this with like a normal equilibrium problem, don't get intimidated by the fact that this is an acid or a base. It's just a chemical reaction, right? It's just equilibrium, right? So that's, I think, the note there. Okay, so we've gone through a ton of content. So let's take a little break, take a breather, use this time to just decompress, breathe, and then when we move on, we will get right into kind of some more meat of this into this unit, which is things like buffers, acid-base reactions, and the scariest topic of all, I think, for students, acid-base titration. So get excited, y'all. We're going to take a 3 or so minute break. All right, y'all, let's get back into it. So the first thing we're going to talk about before we can get into kind of all the scary content is just something called a buffer, right? And a buffer is just a solution that is resistant to changes in pH. So for example, your blood is a buffer, right? A number of other solutions in biology are buffers. A lot of things in biology are buffers. But all that a buffer is just a solution that is made up of an acid and its conjugate base, or vice versa, right? And this is because if you have an acid and its conjugate base, first of all, they'll eventually reach equilibrium with each other, so they won't like eat each other up, which is the problem of why you can't just throw any acid and any base in there. You need an acid and its conjugate, or a base and its conjugate acid. But they can neutralize any added acid and base, right? So if we look at the image on the bottom, we have some AN meaning anion, right? That acid and its conjugate base, the anion. If you add hydrogen, right, it is going to be absorbed by the conjugate base present. And if you add OH minus, it'll be absorbed by the acid present and form water. So in this case, instead of just being like if you were in water and you dropped the strong acid in, or the strong base in, where you see a large change in pH, here the solution is to a point resistant in changes in pH. It doesn't mean pH doesn't change. It just means it won't change as much as if you had done so with a neutral solution, such as just like pure water. So yeah, so we'll do a little bit of practice of identifying buffers in just a second. Okay, so let's take a look at whether or not certain solutions are buffers, right? So a solution of acetic acid and sodium acetate. So this is a buffer, right? And that is because the acetic acid will provide the acid, and sodium acetate, the sodium can kind of be ignored here, it's a spectator. But the acetate ion, that's the conjugate base. We have a conjugate acid-base pair, therefore we have a buffer, right? These two species will reach equilibrium with each other, and eventually we'll have a solution where we can add a bit of acid and have that acid be eaten up by the acetate, or add a base and have that base be eaten up by the acetic acid. So it's a buffer. Next, a solution of ammonia and hydrochloric acid. While this is a mixture of an acid and a base, this is not a buffer because it's not a conjugate acid-base pair. All of the ammonia here would be neutralized by the strong acid, and eventually we would just have a bunch of H+, and we wouldn't have a buffer. It would just be an acidic solution. Next, this is a tricky one, a solution of hydrochloric acid and NaCl, right, just salt. This is not a buffer. You might be going, well, wait, but it's a conjugate acid-base pair. And you're right, but I need this is where it comes into importance that chloride is an insignificant base, right? It's not a base. For all intents and purposes, it's neutral. It's technically a base, but we saw the KB earlier. It's like 10 to the minus 21. It's ridiculously small. So while this is a conjugate acid-base pair, the conjugate base of HCl has negligible basicity. That's a word, basicity, right? Maybe. Meaning this would actually not be a buffer because Cl- isn't a strong enough base to actually eat up any acid that you add. It'll just kind of hang out and be like, I'm just chilling in solution. I'm hanging out. Okay, so now that we understand what a buffer is, how do we find the pH of it, right? We have a mixture of some acid and some conjugate base. What do we do from here? Well, we can use what's called the Henderson-Hasselbalch equation. And this is on your equation sheet. It's personally my personal favorite equation in AP Chem. And you can derive this by rearranging the Ka expression. And if you look it up online, it's not a difficult derivation, but not required for the exam, so I won't go over it. But what it tells us is that the pH of a buffer is equal to the pKa of the acid plus the log of the ratio of the two species, of our conjugate base and our acid. So essentially, the strongest buffer occurs when we have equal concentration of conjugate base and acid, right? Because we won't have any imbalance of that. So because if we have the same concentrations, that equals 1, the log of 1 is 0, the strongest buffer occurs when pH equals pKa. And while that might seem like just a kind of an interesting coincidence, this will become really important when we talk about titrations, which we will in just a second, right? And reading titration curves. But something to note from here is simply that the strongest buffer occurs when the pH of the solution is equal to the pKa of the acid being used, or vice versa, when the pOH is equal to the pKb of the base being used. If you're using, for example, a solution of ammonia and ammonium chloride, that would be a buffer, right? Because we have ammonia and a base, and ammonium, it's conjugate acid. That would form a buffer. In this case, it would probably be smarter to use the pOH form of the Henderson-Hasselbalch. And we'll be using these equations in future problems in just a second. Okay, so now let's talk about actually what happens when we combine acids and bases, right? We have these acids, we have these bases. Let's start playing with them. So we've probably all seen the neutralization reaction of a strong acid and a strong base. For example, HCl and NaOH is the classic example, right? A strong acid and a strong base will both fully dissociate, meaning what we basically just have in the solution is H plus and OH minus floating around, right? Whether that's chloride or bromide or iodide, right? Doesn't really matter here. Same if it is sodium or lithium or potassium. It again doesn't, or calcium, it doesn't matter as long as it's a strong acid and a strong base. So what really matters here is that we have H plus ions reacting with OH minus ions to form water. So in the end, equal concentrations of HCl and NaOH, or strong acid and strong base, will neutralize each other to form a perfectly neutral solution, right? So that's kind of the first one and the first form. Next, we might see what happens if we have a weak acid, like acetic acid, and a strong base, like sodium hydroxide, reacting together. So what we'll see is that this will form CH3COONA, right? Because we'll form, what actually happens is sodium's a spectator here. We have acetic acid reacting with the strong base hydroxide to form water, which isn't included in that ionic, and acetate. And that is the important bit here, right? That when you react a weak base with a strong a weak acid with a strong base, we will form the conjugate base, right? And typically we see these reactions as going fully forward. For all intents and purposes on the AP exam, they will. We might not have all of it going right. We might have an excess reagent, but we typically won't see these in equilibrium. We're not given K values for these equations. We're just told they go fully forward. Similarly, oh, can you go back? Sorry. If we have a strong acid and a weak base, so hydrochloric acid and ammonia, this will form ammonium chloride because the H plus will react with ammonium to form its conjugate base, and chloride, again, whether it's hydrochloric acid, hydrobromic acid, hydroiodic acid, irrelevant here, right? It would all do the same thing. It would form ammonium chloride, ammonium iodide, ammonium bromide. But the net ionic, what's actually happening here is ammonium reacting with the strong acid H plus to form ammonium, right? And again, we might note if this reaction happens where we have some ammonia left and some ammonium left, we'll have a buffer. Same thing with the previous reaction of acetic acid and sodium hydroxide. And that is where buffers come in. When we have to find the pH of these reactions when they occur, we'll get a buffer. So when we're talking about a weak base and a weak acid, those will just react to form kind of the fusion of the two, right? We'll see the H plus pop off of acetate, attach onto the basic NH3 to form NH4, and then we'll form an ionic compound, NH4CH3COO in this case, which is ammonium acetate. These reactions are really crucial to understanding titrations, to understanding just what happens when an acid and base mix. And that's all a titration is. I really want to push that idea. All a titration is an acid-base reaction that we slowly do. They're really not that scary. All right, so speaking of, let's talk about acid-base titrations. Right, the scariest topic in AP chemistry. Quite possibly, it strikes fear into every student I've ever talked to. But they're really not that bad, right? So let's just talk about first, what's a titration? What is a titration, period, right? Not all titrations are acid-base titrations, but for this course, most of them will be, right? Titration is just a lab procedure, right? You could do it in your AP, you might have done it in your AP chemistry class, that involves dripping a titrant of known concentration from a burette into an analyte, or sometimes called a titrand, of unknown concentration until an equivalence point. And the equivalence point is, and this is important, an equivalence point for titration is the point at which the moles of titrant that you've added to the solution equals the moles of analyte or titrand that you had in the flask to begin with, right? So the equation balances out perfectly. You reach the point where you've stoichiometrically balanced it. So for example, a problem we might ask is, we have 6 molar CH3COOH, and we have an unknown concentration of sodium hydroxide. If it takes 10 milliliters of CH3COOH to reach an equal number mole of acetic acid and sodium hydroxide, we can calculate the concentration of sodium hydroxide. And to do so is, well, simply put, we know we used 10 milliliters of 6 molar acetic acid. So we multiply molarity by volume to find moles. And that's the same number of moles of sodium hydroxide, right? Actually, there's a mistake in this problem. We would need the starting volume of sodium hydroxide as well to find the full concentration. And we'll be doing problems like that later, but this is just an introduction. Okay, here we go, right? So taking a look at that problem from before. Suppose we have 6 molar acetic acid and 30 milliliters, there we go, of unknown concentration sodium hydroxide. It takes 10 milliliters of acetic acid to reach an equal number of moles of acetic acid and sodium hydroxide in solution. And from there, we can calculate this concentration of sodium hydroxide. So first thing we do with pretty much any titration is just write out the reaction that's happening. It just helps us kind of think about what's actually happening as we drip it, because it's a weird thing to visualize. But if we just visualize this reaction happening, it becomes infinitely easier, right? We just think about, we have this much acetic acid, this much hydroxide, it creates this much acetate. So we have 6 moles times 10 milliliters of acetic acid, which is 60 millimoles, right? So molarity times milliliters is millimoles. It's typically just easier than writing it like 0.060 moles. It's the same thing as a mole. It's just less, like it's 1,000th of a mole. And that means that in the original 30 milliliter solution, we had 60 millimoles of NaOH. Molarity can be described as moles per liter, or just dividing by 1,000, millimoles per milliliter. Or excuse me, multiplying by 1,000, doing the unit conversion. Millimoles per milliliter. We divide millimoles by milliliters to find that we originally had 2 molar sodium hydroxide solution. So that's an example of a use of titration to find the concentration of that unknown sodium hydroxide. So there is actually an alternative method, and that's to use what's called this formula called MAVA equals MBVB, right? All this is just, again, saying the moles of acid equals the moles of base. It's important to remember our stoichiometric coefficients, though. So technically, there should be little constants in front of both sides of that equation that tell us, how many moles of A do we have for moles of B? Which I don't think there's an example of that in here, but it's just adding a constant to the front, and you'll know when to do it. So using our example before, 6 molar times 10 milliliters equals molar of base times 30 milliliters. We can do the math and do the algebra and solve to find, once again, 2 molar concentration of HCl. Or excuse me, NaOH. Excuse me. All right. So let's take a look at pH and titrations, right? So all we're doing here is just finding the concentrations at the end of an acid-base reaction. It sounds really scary. It sounds really freaky. It's just an acid-base reaction. We've all seen them. They're friendly, right? So for example, we have some titration of acetic acid into NaOH. So a weak acid into a strong base. Well, we know that that sodium is a spectator, and the net ionic is going to look like acetic acid reacting with the hydroxide ion to form acetate and water, but water is kind of ignored here because water is a solvent, so it won't be involved in the equilibrium, or won't be involved in the net ionic. And we know we have 25 milliliters of 0.2 molar acetic acid. Multiply those two numbers to find that we had 5 millimoles, and it's titrated into 40 milliliters of 0.1 molar NaOH. Again, multiply milliliters by molarity to find 4 millimoles, and that's our start. This reaction goes fully forward, so we can just treat this like stoichiometry, right? We eat up all of our limiting reactant. In this case, our limiting reactant is hydroxide, right? We eat up all our hydroxide to form 4 millimoles of CH3COO-. However, we have 1 millimole of acetic acid left in solution. We have a mixture of an acid and its conjugate base. This should immediately set off alarms in all of your heads, right? When you hear the words acid and conjugate base, right, what word should be fitting into your head? Drop it in the chat. When you hear acid and conjugate base, or base and conjugate acid, right? Buffer, right? This is just a buffer, and we know how to find the pH of a buffer, right? That is to use the Henderson-Hasselbalch equation, which we know our total volume is 65 milliliters. We plug all these numbers into the Henderson-Hasselbalch, and we find our pH. That's all a pH is, or all a titration is. It's just a reaction. It's just a reaction that is specially done to find concentration typically. But in this case, we can calculate the pH by knowing how much acetic acid has reacted with how much sodium hydroxide. Simple as that. So let's take a look at another one. Okay, so for a weak acid, or for a weak acid strong base, or strong acid weak base titration, we have a half-equivalence point. And that is the point where the moles of acid is equal to the moles of conjugate base, or vice versa. And that is because we form a buffer, and we'll slowly keep creating conjugate base until the moles of acid equals the moles of conjugate base. That is our strongest buffer, right? And this can kind of be thought of like, we'll always reach a half-equivalence point. And this is where our maximum strength buffer occurs, which is where pH equals pKa. So for example, what is the pH when 60 milliliters of 10 molar acetic acid is titrated into 15 milliliters of 0.2 molar sodium hydroxide? And we're given the Ka of acetic acid, right? So again, we calculate our moles of acid and moles of base by multiplying molarity by volume. We get 6 millimoles of acetic acid, 3 millimoles of hydroxide, and we start with no acetate. We have a reaction go fully forward, do the stoichiometry, and we find we have 3 millimoles of CH3COOH, 3 millimoles of acetate in a total 75 milliliter solution. We plug all those numbers into the Henderson-Hasselbalch, and we find that pH equals pKa at 4.74. So that is kind of an interesting consequence of titrations. So let's take a look at a titration curve, right? All a titration curve is tracking the pH of our analyte, our titrand, what we're dripping into, as we add our titrant, right? So in this case, we start with some acid, right? We start with some weak acid, and I'll tell you why I know it's a weak acid, right? We know it's a weak acid. We start with that in our flask, and we're dripping in some strong base, call it sodium hydroxide, right? As we add sodium hydroxide, we can plot what the pH is, and at some point, right, in this case, 50 milliliters, at that point, we reach the equivalence point, and we know it's the equivalence point because that is the point where all of our acid has been eaten up by base, right? We're dripping in the space, and every time we drip in the base, we slowly chip away at our acid, right? We slowly are reacting with that acid to form water and a salt. You know, acid being eaten up, strong base. And once we reach that equivalence point, eventually the hydroxide created by our excess strong base will take over, and we'll have an incredibly high pH relative, right? So in this case, the pH at our equilibrium point is slightly basic, and that's because we're titrating in a strong base. But if we have a strong acid weak base titration, for example, hydrochloric acid being dripped into an ammonia solution, we'll have an acidic equivalence point. If we have a strong base weak acid, such as in this chart right here, a basic equivalence point, a strong acid strong base will be neutral. Again, remember, because the strong acid strong base will fully neutralize each other. And then a weak acid weak base titration, it depends, and I don't think this is tested. Please correct me in the chat if it is tested, but it's very rarely tested. I've never seen it. And again, we can just interpret from these titration curves what's actually going on. So I want you to note that the titration curve before the equivalence point is a little bit flat, right? You might be thinking, well, why is that, right? And once again, right, drop in the chat, what would happen? What would we have if we have some solution that is slightly, less resistant to changes in pH? What alarm should that be setting off in your head, right? Again, buffer. buffer. I don't know why I kind of like just getting the chat to spam buffer. And yes, weak acid strong base is their favorite. They love weak acid strong base titrations. Also, I saw a question about millimoles in the chat. That's just a simplification, right? Millimoles is just our way. It's all a millimole is 1/1000th of a mole. It's just another unit. So millimoles per milliliter is the same as moles per liter. It just makes the math a little easier because you're dealing with like 60 instead of 0.006 or whatever. You can do it in moles per liter if you want. You just might get a bunch of decimals, right? But so we can note that this, before the equivalence point, we have our buffer region, right? And the halfway point to the equivalence point at 25 milliliters is where A, that curve is flattest, meaning we have our strongest buffer, and B, the point where pH is roughly equal, or actually exactly equal to pKa, right? It's just we can kind of estimate it here because we don't have the exact numbers. But pH equals pKa, and that's an incredibly important point to note. So we're dripping in our strong base. We have a buffer. Suddenly, we reach the point where our moles of acid is equal to our moles of conjugate base. Strongest buffer possible. That is at our halfway equivalence point. Then we keep adding base, and we reach our equivalence point. Moles of acid equals moles of base. Boom, pH shoots up. Right, you can't see it, but I went like that. Right, pH jumps up because now suddenly that hydroxide that we're adding from the strong base is taken over, right? We have hydroxide. It's like the thing, right? And therefore, it shoots up, and then we continue on a relatively shallow path of a rising titration, or a rising pH. Right, so here is the titration of a strong acid into a strong base, right? So here we have NaOH into HCl or something, and we can see at the equivalence point, it's 7, it's neutral. But in this case, we're adding NaOH to a weak acid. That OH is going to be more powerful because it's not all going to be eaten up by the H+, because we have a weak acid, and we'll have a slightly basic solution at the equivalence point. So that's something to note, and you might be asked about. All right. So here's a sample problem that's kind of ripped straight from an FRQ. Oh, Oh wait, can we go back? Sorry, I have to explain the question. Okay, so in this case, we're asked to approximate the Ka of the given acid. We don't know the acid. Of the given acid used in this titration of potassium hydroxide, some strong base, into this weak acid, right? So what we do is we know our equivalence point is at 20 because we can see it on the chart, meaning our halfway equivalence point is at 10, right? Halfway there. We can look at where the graph is at the y value at 10 milliliters, and that gives us approximately 3.4, right? You'll be given a little bit of leeway on 0.1 differences, but roughly 3.4. So pKa is 3.4, negative log of Ka is 3.4, solve for Ka, and we get our Ka. So that's another important thing we can use titrations for. All right, so let's move into a quiz, right? Test some of that knowledge. All right, so feel free to join up. Let me drop the, oh, sorry, the music just hit me. I'm going to drop the link. Oh, Adam beat me to it. All right, and so we'll get it started relatively soon. All right, let's get this quiz started. People can join as they join up. Okay, so 300 milliliters of 1 molar HCl is added to 100 milliliters of 1 molar sodium hydroxide. What is the pH of the resulting solution? I want to make a note. Quick hint. This is just an acid-base reaction. So write out the reaction and then do the stoichiometry. You heard nothing though. I didn't say that. All right, let's see. All right, so we see that the pH is 0.3, right? So in this case, we have 300 millimoles of hydrochloric acid reacting with 100 millimoles of NaOH. So we can do the stoichiometry and find our concentration of H plus and OH, and we can find the pH from there. So same as any other reaction. All right. So which of the following can form a buffer solution? We've got 4 options, and I think I've hammered in what phrase should set off your buffer alarms. So let's see how y'all feel about this. All right, so looks like most people got this right. It is a solution of sodium acetate and acetic acid, right? Again, acetate and acetic acid. When you see a conjugate acid or an acid in its conjugate base or base in its conjugate acid, your brain should immediately go, there's probably a buffer somewhere around here, right? Let's break down the other answers though. Ammonium acetate and ammonium nitrate. Well, we'll have a bunch of ammonium and some acetate, some nitrate, but we won't have a conjugate acid base pair, so it's not a buffer. Sodium acetate and hydrochloric acid in water. Again, there's no conjugate acid base pair here, right? And ammonia and sodium hydroxide, no conjugate acid base pair. So boom. All right. Oh, this is something I think we forgot to go over. I'll quickly go over this, right? Electronegativity can impact the way that acids and bases are strengthened, and that is because if we're talking about, for example, hydrogen versus fluorine. Give me 1 second here. Okay. So when we're talking about the molecular structure of acids and bases, right? We're talking about the molecular structure of acids and bases. We want to remember that the strength at which those hydrogens are held onto that molecule is based on the electronegativity of the molecule, right? So, or of the atoms in the molecule. So if you have electrons being pulled in, it'll probably be a weaker base because it is harder to rip off those H pluses. Yeah, this is very much a Unit 3 question, sort of. Yeah, so we can see NF3 is a weaker base than NH3 because the greater electronegativity of F compared to H, right? So typically, stronger electronegativity will hold on those hydrogens, or those, whatever the base forming thing is. And so if you can't dissociate that, you can't, right? It's hard to dissociate. That will typically make it a weaker acid or base. So that's how molecular structure relates to acids and bases. This is not a super tested topic. All right, but nice job on the quiz overall. All right, so let's get right into our next unit and the final unit of AP Chemistry, and that is the applications of thermodynamics. Let's see, I think we have someone else hosting that. All right, so let's just jump right in, right? Let's talk about how thermodynamics relates to this whole class. Okay, so the first thing we want to talk about with Unit 9 is entropy, right? What is entropy? Entropy is a measure of disorder in a system. It is the amount of disorder in a system. It is the amount of randomness in a system, and reactions can either increase or decrease entropy, right? Excuse me. Right, so reactions might create disorder, they might create order, and entropy is designated by S, right? I'm not actually sure why. That's kind of a weird notation, but chemists use it, so we're going to use it. All entropy is kind of weird. It's just basically how many. It has something to do with like states of a system. So if a system is more random, there's more chaos going on. That means that it is higher entropy versus, for example, a very rigid structure. For example, a crystalline solid will have low entropy. A gas, everything's flying around, so it's more entropic, I think is the word. All right, so I'm going to pass it off to Shreyas to talk about the rest of thermodynamics.
Hi guys, sorry about that. So there are 3 laws of thermodynamics. So the first law of thermodynamics is called the law of conservation of energy, and that law says that energy can only change forms and cannot be created or destroyed. This is a pretty famous law, a thermodynamic law, the law of conservation of energy, and I know a lot of people know this from some other science classes too. So basically, the first law is that the energy can only change forms; it cannot be created or destroyed. So yeah. And in Law 2 is that in isolated systems, energy quality and entropy can increase. And there's two parts to this. Part one is that when energy is transformed from one form to another, some of the energy is lost as heat to the environment. And part two is where entropy tends to either rise or remain constant in an isolated system. And the overall S must be greater than or equal to 0 for any spontaneous process. So there are two parts to Law 2, and those are that. And the third law of thermodynamics is that when entropy is 0 at all times when the temperature is the absolute 0. So when it's 0 Kelvin, the entropy is 0. And yeah, I'll give you a minute to look at that slide. So let's get a little familiar with the sorry, I don't know what you call it, the variables, kind of the symbols for entropy. So the first one is just the absolute form of entropy, and the second one is delta of entropy, so it's a change of entropy, and the formula for this is the sum of the products minus the sum of the reactants, sum of the absolute form of entropy of the products minus the sum of the absolute form of entropy of the reactants. And sometimes people get a little bit mixed up with them too, but this is just a quick reminder what they are. And the degree symbol, it means that it is at standard conditions, and standard conditions, just as a reminder, is 1 atm of pressure and 273 Kelvin. Our next topic is thermodynamic favorability. So thermodynamic favorability is what is to determine whether or not a reaction will be spontaneous or not. Basically, spontaneous reactions are favored in a thermodynamically, and non-spontaneous reactions are I think aren't seen as favorably. I think I wrote that wrong. So enthalpy and entropy, sorry. So first we'll have we're going to be talking about enthalpy change. And basically enthalpy change is the change in the heat of the system relative to the surroundings due to a reaction. And I think we already went over this, but it's just a refresher. So basically delta H, when delta H is negative, that means it's exothermic because it's losing heat to its surroundings. And when delta H is positive, it's gaining energy from the surroundings, so it's becoming endothermic. So that means it's endothermic. And next, we're going to be talking about entropy change, which is delta S. The change which is the change of disorder in the system. So when delta S is positive, that means the disorder in our system is increasing. And when delta S is negative, the disorder in our system is decreasing. So I just want to bring back a point is that when there are certain changes of, I want to talk about like the changes of state. So when it's going from solid to liquid and liquid to gas, the entropy change is positive, so the disorder is increasing. And when it's going from gas to liquid to solid, that's when the delta S is negative and the disorder is decreasing. I just want to talk about that again, just to make sure that, just to make sure that people remember that, because that's an important point. So it's time to take a brain break. We'll take a brain break for a couple of minutes, and we will restart. Okay, so we're back from our brain break and we're ready to start. So our next topic is Gibbs free energy. So basically, what is Gibbs free energy? So the formula for Gibbs free energy is delta G is equal to delta H minus temperature times delta S. So basically, Gibbs free energy is an equation, and basically we're trying to find the change in Gibbs free energy. And Gibbs free energy basically tells us the amount of energy that's available to do work. And this is as a result of the function of delta H and delta S. So basically, there is a table right as you can see the table to the right, there's a table to the right. I don't believe on the AP exams they'll ask you to calculate delta G that much, but don't quote me on that. So basically basically the formula is delta G is equal to delta H minus temperature times delta S, and temperatures will always be in Kelvin, I believe, too. And with this, we'll be able to know if the spontaneity of a reaction. So if delta H is positive and delta S is negative, then we know that delta G will be positive, so we can say that it's not spontaneous. And if we find out that delta H is negative and delta S is positive, and we find out that then we'll know that delta G will be negative, and then we can say it's spontaneous. So as you can see, there's a table to the right which tells us the spontaneous and non-spontaneous, but this thing to remember are the last two. The last two where when delta H and delta S are both negative, and delta G can be either positive or negative, and it depends on the temperature. If there's a low temperature, it'll be spontaneous, and if there's a high temperature, it'll be non-spontaneous. So keep an eye out for that, and if you see that delta H and delta S are both positive, then you need to see whether it's low temperature and high temperature again, because if it's low temperature, it's not spontaneous. Sorry, if it's low temperature, it's non-spontaneous, and if it's high temperature, it's spontaneous. So basically, if delta G is positive, it's non-spontaneous, and if delta G is negative, it is spontaneous. And our next topic is kinetics. And we did touch upon kinetics a little bit beforehand. And basically, kinetics is the study of the rate of a reaction. We measure the rate of the reaction by measuring the change in the concentration of reactions over time. So basically, the formula is R is equal to delta concentration of A over delta T. So basically, when we have higher R values, we can note that there's a more rapid loss of reactants and product production, and vice versa. Too, for when we have lower R values, we can denote there's a less rapid loss of reactants and product production. And that's pretty much it for kinetics. So basically, chemical reactions will take place when molecules collide with each other at the proper angle, speed, and energy. And that's according to the kinetic molecular theory, which is a theory that you need to know because chemical reactions only occur when molecules collide with each other at a certain angle, speed, and energy. And the energy that's needed to cause a chemical reaction is called the activation energy. And it's harder for a reaction to proceed at a observable pace at higher activation energies. So basically, if the activation energy is higher, it's harder for a reaction to go faster, I guess. So those are 3 points that you definitely want to keep in mind for Unit 9. Our next topic is electrochemistry. So basically, electrochemistry is the study of redox processes and how they can be used to generate electrical energy. And there are, we're going to be talking about, I believe, first we're going to be talking about the galvanic slash voltaic cells. So basically, a galvanic cell is when there is energy released by spontaneous redox reactions and is converted into electrical energy. And basically, it's a tank where we separate the negative anode and the cathode, and there's electrons going from the anode to the cathode. Yeah. So for a galvanic cell, we separate the anode and the cathode, and basically their electrons will be going from the anode to the cathode, and there will be a cell bridge in between the two separated areas, and the voltage will be used to drive a non-spontaneous redox reaction. So yeah, so this is, as you can see on the right, there is a galvanic cell, and I just want to point out the different components of a galvanic cell. So on the left of a galvanic cell, you see that there is an anode, and from the anode, electrons are traveling to the cathode. So always remember that electrons always travel from the anode to the cathode in a galvanic cell, and in a electrolytic cell too. And there's another type of cell called the electrolytic cell, and the electrolytic cell is where non-spontaneous redox processes occur, and the E cell is less than 0. So the difference between a galvanic cell and electrolytic cell is that in a galvanic cell, the E cell is greater than 0, and the electrolytic cell is less than 0. And electrical energy from the electrolytic cell is used to drive non-spontaneous redox processes. And our next topic is coupled reactions. So basically, when there's no form of external energy, thermodynamically unfavorable reactions will not take place because they won't happen naturally. So non-spontaneous processes can be supported by external sources of energy, and electricity is usually a typical energy source, and it can be used to accelerate non-spontaneous processes. And non-spontaneous redox reactions can occur with the use of electrical energy. And usually we can do linked reactions, and that's coupled reactions, which is another approach to induce spontaneous behavior in non-spontaneous responses. And coupled reactions basically combine two types of reaction that share an intermediate, a spontaneous and a non-spontaneous. So now it's quiz time, and let's get started. So let's get started with our first question, and it says, which of the following reactions is an entropy-driven reaction? And we will give you a couple, we'll give you some time to do this problem, and then we'll get back to us. We will get back to you guys with the answer.
Hey guys. Yep, it's quiz time. It's one of my favorite times. Since I'm taking the AP Chem exam, I better be able to answer these questions too. So I'm gonna try to solve it with you guys. Well, it looks like a majority of us pretty much answered it, so let's review the answer.
Wow, so it looks like most of us didn't get that right. So basically, the question asked, which of the following reactions is entropy driven? And the answer is the dissolution of a gas in a liquid. And yeah, sorry. And yeah, most of us answered the combustion of a hydrocarbon to form carbon dioxide and water. And
it's pretty much like when we have a dissolution of gas, we're going from, let's say, like 1 mole of a gas, and then we're creating more moles. So when we create more moles of gas, that creates more entropy. Now, a lot of people answer the combustion of hydrocarbon to form carbon dioxide and water, and that is pretty tricky, but you only have carbon dioxide, and it's most likely going to be in gas form, but water, we don't really know if water is going to be in gas form. Usually it's going to be in liquid form, or the aqueous form. So that's why we have more gas moles equals more entropy. That is the only way that we're going to increase entropy. So now let's move on to the next
so
question.
when we change states from solid to liquid and liquid to gas, entropy increases. So our next question says, which of the following is true about the relationship between the energy released from a spontaneous reaction and the energy required for a non-spontaneous reaction to occur? And we'll give you a couple of seconds to answer the question, and then we'll reveal the answer.
All right, let's just reveal the answer.
Most of us got that right, and the correct answer is the energy released from a spontaneous reaction can be used to drive a non-spontaneous reaction, and this is coupled reactions where we combine a spontaneous reaction and a non-spontaneous reaction to basically give an energy source to the non-spontaneous reaction.
Okay, so we got some answers back from question 1, and question 1 was incorrect. You guys are right about the hydrocarbon one, and just like you guys, I'm learning as well. So it's a dissolution of gas in a liquid that forms a solution, so there would be less gas moles. So that's my bad on me, and you guys are right on the hydrocarbon part. And when we have that combustion, we're increasing the amount of gas moles that we have. So number 1 was D, and you guys were correct on that part. So let's keep on moving.
Our next question says, which of the following is true about the anode and cathode in a galvanic cell? And we'll give you guys a couple of seconds to answer this again, and then we'll reveal the answer.
Let's go ahead and reveal the answer. And there we go.
The answer is B, and 89% of us got that, so that's really good. So the question was asking, which of the following is true about the anode and cathode in a galvanic cell? And B says the anode is where oxidation occurs, and the cathode is where reduction occurs. And we know this because the electron goes from the anode to the cathode, which means that oxidation will occur in the anode and the cathode gains electron. So that means that's where reduction occurs.
All right, and that concludes our quiz. And let me switch tabs over here. Okay, so we have a quick survey down there for the Google Forms, and all right, so we have that quick survey, and you guys can answer that real quick. But I want to break down some of the questions that we had, especially for the Unit 6 quiz, and specifically the question 2 for the Unit 6 quiz. So, so far, like when Shreyas was talking, I've been cooking a little, and I want to show you guys what I've been working on. So, let me turn on light over here. All right, so in question 2, we had the we were given the mass of the metal, and it was like 55 grams, and we were given the temperatures. So when we're solving that question, we want to make Q equal Q. I don't know if that's shown correctly. I'll try to, maybe it's mirrored. I don't know. On my side, it looks a little different, but over here we have negative Q equals Q. And that's how we're going to set up the whole thing. So we have negative MCAT equals MCAT. And when we plug in our values, we have 55 grams of our metal, and we have our C, which it's not given, so we'll have to find that. And we're given our temperature, and it's all changing temperature is always final minus initial. So we had our final temperature as 30. So it's 30 minus 35. So that would be negative 5. And over here on the water, we were given 50 grams of water. The specific heat capacity of water is 4.18. Now, the AP exam will usually tell you that, but I think it should also be in your AP chemistry formula sheet. And over here, our final temperature was 30. Our initial temperature was 20, so that'd be 10. And when you calculate for the side on the water, it's going to be 2090. I believe that's joules over Celsius, or that's just joules. And then over here, we're going to have negative 275 C. We still have that variable. So basic algebra, we isolate the variable by moving negative 275 divided and have 2090 divided by negative 275. And we would get negative 7.6. But remember, heat capacity cannot be negative, so it will be 7.6. And we need it to be positive so that we can make sure that our negative Q, our negative heat, equals our heat. So that's how you solve question 2. And that wasn't the answer choice, so it was a fault on us. So sometimes our quizzes aren't the best, so it happens. And that's pretty much the explanation for the question for quiz 2, or quiz 6, the question 2. And when you see a question like that, when you're not given the specific enthalpy, like if Q is not given, then and you're trying to solve it, you always want to have it equal each other. You always want to find different ways to solve it, and you want to be you want to be able to solve these types of questions. And there's also questions of Unit 6. There's the delta H of the reaction. And to solve that, it was like heat of fusion. That's what it was. So it's heat of fusion, and to find the delta H for that, it's heat of fusion times the number of moles, and that gets you your number. So you always want to work with what you're given. And I want to look at the Unit 7 quiz real quick. I'm going to have to pull that up. Okay, so, or the Unit 7 quiz. So let me share that real quick. Okay, so I'm gonna move over to stage left over here. Okay, so I think this was one of our questions that we had, and this was setting up ice tables. So I didn't really cook on this one. I've been spending my time cooking on the Unit 6 question, but I think for this one it was 1.1 moles. And in the chat, if you guys want to explain why that was, that would be great, because unfortunately I didn't dedicate a lot of time for this, but in the night 5, I will definitely talk about this question, and we'll definitely talk about ice tables. And Unit 4, we have I had pre-recorded some videos by some FRQs having titration, ice tables, the whole shebang. And I think, oh, there's the music again. All right, so the question 3, I think we got this, but let's just let me click on this one. Let me get this one real quick. So we have, let me do this, B squared, and then we have A. All right, so here's what our sort of setup would look like. So we have our equilibrium constant. So we're setting up as normal, and we're trying to find our C. We're trying to find that we're trying to isolate for C. So all we have to do is just basic algebra. So from here, we would multiply the B squared times A over to the K. So then that would make K B squared A, and that'll equal C squared D, and that's what we got so far. And from here, we move over the D and just square. I believe we square root it, so our answer would be state D. And this isn't the answers that you guys got. It's just showing some of the answers that were just shown. But let me move to stage left so you guys can see this better. So we have the square root of K times A times B squared over D. So that's just basic algebra for solving it. And let me unshare my screen so then we can have Anuva, Elias, and we can have Dylan and Shreyas and all of us just answer some questions.
This is our like Avengers Assemble moment here.
Oh yeah, or like Power Rangers.
Yeah, form of a hydrogen atom. I don't know if that was too dated of a Power Rangers reference. I don't know if that was
or
like
the Teenage Mutant Ninja Turtles. What I call Michelangelo.
All right.
Hi everyone.
Chemistry.
So I think we need to go over a little bit about E-cell, just to brush up on that. So basically, E-cell is like the measure of electrical potential that's in a chemical reaction that can be produced when like two half cells in a galvanic voltage cell, I believe it's called, are connected together. And then so E cell equals E cathode minus E anode. So let me see if I can like find
I can pull one up. I've got one.
Okay.
Ready. Okay. I'm gonna share my screen here. I'm about to pull up an online whiteboard. Please forgive my handwriting. I'm on a Mac trackpad right now. I'm trying. But
everyone went to the wing.
There we go. Sorry. All right.
Wait, let's move us back.
Okay. So we have a redox reaction here, right? We have gold 3 reacting with copper. Oop, wait. I think let me move back here, especially. Oh boy. Oh boy. We're all flying around here. Okay, good. We're all here. Okay, so we have gold 3 reacting with just neutral copper to form gold and 3 copper plus ions, right? In this case, first, let's identify what is being reduced, what is being oxidized. So we need to look at our oxidation numbers. In this case, the oxidation number of gold goes from 3 to 0, so it's being reduced, right? It is gaining electrons, it is reducing in charge. Copper goes from copper to copper plus, it's being oxidized, right? So we can split this up into 2 half reactions, right? That is the first step for finding these potentials. So we have A3 plus reacting with 3 electrons to form, with 3 electrons to form a gold atom. And we have 3 copper reacting to form 3 copper plus 3 electrons. Right? Let me make sure that's right. I'm doing this on the fly, so I might be screwing this up. We have 3 copper reacting to form. Yep. Okay, perfect. Right, because this balances
Yeah,
out.
you're good.
Okay. I had to make like double, triple sure. So the next step is to figure out the cell potentials for each of these half reactions. And you might be going, how do I calculate that? I don't know how to calculate that. We've got a handy dandy table right here of reduction potentials, right? So we can just use our table. So we can look first at the reduction of gold 3, which is all the way up here, to form gold. That has a reduction potential, an E of, actually it's an E naught, I think, assuming we're at standard temperature and pressure and all that, of 1.5 volts. And voltage is like, all the E&M people in here are going to like make their skin crawl when I say that it's like force, but electrons. I'm not a physics person, I'm a history major. And next we can look for copper. Well, if we look for neutral copper, here we go. Wait, I can't find it. And that's because copper here is being oxidized. So we need to look on the opposite side and find copper. And we see copper forming copper and electron, which has an E of 0.52. We have to flip it to find negative 0.52. And I just want to confirm from y'all, because it's been a minute since I've done this. Do I have to multiply this by anything because this is multiplied? I believe not.
Mm-mm.
No. Okay, perfect. So the next thing we're going to do is add together these cell potentials to find a total cell potential, right? So each cell of 1.5 minus 0.52, which is 0.98.
Oh, by the way, it's you do the cathode minus the anode, so then it would be 1.5 plus 0.52
Yes. Well,
because it's a double negative.
is it because we flipped it already?
Oh, sorry.
No, you're good. You're good. I'm pretty sure it's cathode minus anode, because if we just have this, because this reaction wouldn't be happening at the anode, it would be the reverse reaction, this reduction happening. So
Right, you're so right. Yeah.
Yeah. So I think this math is right. Let me plug this into a calculator real quick to make sure I'm not dumb. I'm not dumb. So from here, we have an E cell of 0.98. Great. What does that tell us about this redox reaction? Right? What can that tell us? I'm pulling up an equation right now because I can't remember it. But it can tell us something about the spontaneity of this redox reaction. In particular, we can use the equation. Oh, geez, it's not letting me copy paste. Oh no. Okay, there's our equation, and it's on top of things. This is like my second time using this thing. 1 second. There we go. Right. Delta G naught equals negative NF E of the cell. Right. This is an equation that relates Gibbs free energy change to our cell potential. N is the number of moles of electrons that are moving. Well, that's 3 moles times Faraday's constant, which is a number that I totally know, but like I'm gonna look it up because
it's 96,485 coulombs per mole.
Thank you. Yeah, I knew that, but I just want to make sure you guys knew. Times the E naught of cell, 0.98.
That's
And
on the formula sheet, by the way.
It is. You do not have to have that memorized. And this gives us negative this number. So you guys can't see my calculator. That joules which will give us negative 283.7 using sig fig math that I totally know, kilojoules. Right? Yeah. And so that tells us the delta G. So what does that, the sign of that delta G, tell us about the spontaneity of this reaction? We have a negative delta G. So in the chat, tell me, will this redox reaction happen spontaneously? Yep, spontaneous, spontaneous, spontaneous. Perfect.
Yay.
Right? Amazing. And actually a quick way to see this without having to go through the whole process of calculating delta G naught is just to look and note if this E cell, because these are typically, right, you'll always have a positive number of electrons moving, and this is a constant. If this number is negative, this number will be positive, meaning non-spontaneous. If this number is positive, we have a spontaneous reaction. Now let's take this one step further because I'm crazy. Now let's look at how we can calculate the equilibrium constant for this reaction, right? So we have another equation that's pretty central to Unit 9, and that is that delta G equals negative RT ln K, right? Where R is our thermodynamic constant, so 0.082, or excuse me, it's 8.314 joule per mole Kelvin, I think. Can you check that for me? I used to have that one memorized. Times
Yeah. Yeah.
Okay, fair. We're at standard temperature pressure, so 25 times negative.
Oh, no, you're good. You're good. Yeah, sorry.
There you go. Times log of K, and that is going to equal, what was it, negative 283.7. Right, and if I'm looking at this, so if there are any questions, feel free to shout them out at me if I'm like going too fast.
Although I do think that it's not 25, it is
273.
298.
Okay, sorry. Yep, this has to be Kelvin. Thank you. Right, because Kelvin will cancel out Kelvin and joules will cancel. Yeah. Okay. Then we can solve, and I won't go through all the algebra, but from there you can pretty simply find our K value, which should be pretty high. So that's kind of the general process of this. And let me see if I can find an image actually. There's like a triangle of equations that is very fun to look at. Yeah, here it is. Look at that. Let me drop that right here. And these are the equations that relate E cell, delta G, and K, which can help us talk about how these three things are related, right? They're all the same concept of telling us, well, what is the movement of these electrons? What is the spontaneity of this reaction? How far will this reaction go? They are all kind of this. It's like, oh God, it's like, I'm thinking of that TikTok sounds where it's like, I can't remember what it says, but it's like same thing, different shape or something. They're all the same idea of asking, will this reaction happen and how far does it go, right? The higher the voltage, the more powerful this reaction, right? The more spontaneous, the more forward it will go because it's spontaneously happens. It doesn't require any free energy input. So that's kind of the big picture around electrochemistry and cell potentials. All a galvanic cell is a way of actually putting this together in a physical form, right? So let me pull up an image here and I'll run through it quickly because I know we're cutting for time, so I apologize. So this is a galvanic cell, right? All that's happening here is a redox reaction. We are having copper reacting with silver, right? So copper is being oxidized to form copper 2+, right? Yes. It's being oxidized. Electrons are moving through the voltmeter and reducing this silver plus in the silver nitrate solution. And the reason this happens is because that reaction is spontaneous. We could go through the math and do it, but I'll leave that as a practice problem. And you should find that this reaction will occur spontaneously because of our positive voltage of 0.46. That's all all this is. There's one quick little piece, and that's the salt bridge. All the salt bridge does is keep the electrons moving. It keeps the ions flowing because eventually the electrons will just all move over to one side. We need to keep ions flowing for the electricity to continue flowing through the system. That's all a salt bridge is. It just connects everything up. So that's the big picture of galvanic cells. I know that was very quick and very scrappy.
And to people asking in the chat, to those of y'all who are asking for a screenshot, keep in mind that this will be in the recording that will be released immediately after 10 o'clock.
Yeah. Also, feel free to take a screenshot just right now. Like, I'll leave this up for I'll give you guys 10 seconds.
Yeah.
Actually, I was gonna say I was just gonna say I can address a couple of the top Q&A questions real quick while we leave that up because they don't involve showing anything really.
Perfect.
So our top one with 21 votes. Can we go over more graphical analysis this weekend? Considering that this question was here from before the live stream started, I can tell that this is something that y'all are a little anxious about. So as a group that we are either tonight or tomorrow going to throw in some multiple choice questions regarding graph analysis. And the reason that we're putting it in tomorrow is one, so you guys can get that stress relief. We know that not understanding something can be, why are y'all throwing more votes in as I'm talking about it? Anyways, knowing that you're stressed about it, getting it over with and learning the material sooner will definitely help bring some stress relief off. But also it goes very, very well with the multiple choice. It will help us, or help y'all rather, understand how the multiple choice section works while also getting that graphical analysis. And then for the second one, how do we improve chem confidence, such as overthinking, changing behaviors, and or being anxious? I want to let some of my other co-hosts take that question first. I'm curious what y'all have to say, like first thing that comes to mind.
I think for me, we're at a very critical point in the study process right now where like it's pretty hard to build confidence by just doing problem after problem after problem because we're so close that if you experience something like where you don't get something right, it tends to spiral into a confidence issue. I think the biggest thing to do is just trust that you know what you're talking about. Specifically with topics where it's like, you know it, you can trust yourself. I think it's worth kind of going into that exam room. If you go into the exam room and sit down with the mindset of, I'm going to fail, I'm about to get a 1 on this exam, you will be more nervous than even if you fake it, even if you're faking it. I have walked into so many AP exams, faked it, and gone, I'm going to get a 5. I'm going to get a 5. I'm going to get a 5.
Yep.
And then gotten a 5.
That was me with Lang last year. I'm gonna be real.
Exactly. You need to, I'm gonna tell a quick story here. I think something to note is that one question on the AP exam for 99% of students is not going to have a drastic impact on your score, right? When I took my AP exam back in 2019, I got to the third FRQ, got stumped for like 15 minutes, had a brief legitimate brief panic attack in my chair, but moved on, right? You might get stressed during this exam, but then you have to remember 1 point is not for 99% of these questions or these tests. 1 point is not going to be the big difference for you, right? There'll be some edge cases, but for most students. So it's worth remembering that you don't want to dwell on that one question and that the exam is pretty spread out. If you're good with electrochem, but bad at intermolecular forces, remembering that both of those topics will be on the exam. And so you'll have your strengths and your weaknesses. So lean on your strengths, not your weaknesses.
And hey, I noticed there's a comment I want to point out while we're talking about it. Ruth, you're talking about us being super smart, but I want to make a point real quick. All of us have been trained to become the specialists at the units that we talk about. So you'll notice that, a lot of us do have a basic understanding of a lot of it, but I promise you, if you looked me in the eyes and told me to explain Unit 5 to you, I would straight up tell you no, because I was sick for all of Unit 5 and I barely understand it now. There are going to be things that you're weaker with, and there are going to be things that you're stronger with. And that is completely okay. It's okay to have specialties. It's okay to be stronger in certain spots. If anything, the negativity that telling yourself, I don't understand any of this because I don't understand one of these things is going to be much more of a weighing factor on you than just taking a deep breath and understanding, I don't have to be perfect. I am human. Everyone around me is human. I don't even have to pass. I will still be a good student. And I will still be a smart individual because I have shown the ambition and the passion to get through this class as a whole.
Also, for FRQs, they have partial credit. So even if you in the end don't understand how to answer the question, literally just write as much work as you can. Try to get to the answer as much as you can, but it will all have partial credit. So it's not like, oh, this 6-point part, I don't think there's a 6-point part, but it might be up to 4 points. You're like, oh, this answer is totally wrong. As long as you show work and you are on the right track, you're going to get some partial credit.
I kind of wanted to move away from that because we had a bunch of questions about YQ equals negative Q for that one question that I was breaking down on the whiteboard. So it's because we're talking about the first law of thermodynamics, which is talking about how energy is conserved and can be transferred. It's obviously going to be transferred, cannot be destroyed or broken. So I have a piece of paper with me right here, and you can see that it states that when we have a water of the enthalpy of water, and I know the lighting isn't the best, the energy from the metal or the heat transfer from the hot metal to the colder water will be the same. So it's moving from the heat of the metal into the cold water, and that's why it's a movement from a positive Q to a negative Q. And you have to count that. And it's usually with questions when you have a metal dipped in the water. So I just wanted to talk about that question real quick. Thanks, guys.
Yeah, no, I'm
What's
gonna
our
be
next-
honest. Sorry.
Oh no, you good.
I was just gonna say, like, people are like asking me why I'm laughing because I'm reading y'all's comments, and frankly, I laugh at a lot of them because they're funny. They make me giggle. Y'all are funny people.
To answer Ruth's question, no, not really, because I'm trying to be a surgeon. I don't want to. I don't really want to do much teaching. I mean, maybe like teaching about anatomy, physiology, and pathophysiology, because that's what I like more. But I'm kind of like Dylan, where I'm just taking chemistry, but I have a different major, different passion.
Yeah, me and Jahong are both taking the exam this year with you guys, so like we're in it with you guys.
Mhm.
Honestly, I'm with y'all too. I didn't take it this year, but I'm gonna be real. I got a 4, and honestly, I'm making a point of that to say like you can understand the material and still struggle as a test taker. Not getting a 5 is okay. Doing your best is the most important part here. I'm not the best STEM test taker. That's cool. I can still teach you guys the concepts while not getting the perfect score, and that's cool.
Yeah, I think it's for
And one exam doesn't define anything.
You beat me to it, Shreyas. This exam does not define you. You can be a chem major, get a PhD in chemistry, be like a Nobel Prize winning chemist, and have gotten a 1 on this exam or a 5. It doesn't matter. It's not there's no relationship.
We have 3 more minutes. Do we want to pull up the Q&A tab again? Or do we want to
we-
start winding down? We could do one more,
I
or
think
we can
we
just wind
should
down.
start winding down.
I was
Okay,
gonna wind
yeah.
down.
That's fair.
Yeah, we'll answer more Q&A questions. We'll have more time for it on nights 3 and 4, and then night 5 is definitely like all up to you guys about like what you guys want to review. So yeah, we'll see you guys within the next 3 days, and we're here for you guys.
You guys are going to do amazing, genuinely.
Y'all are gonna
Like,
kill this exam.
I know it's anxiety inducing, and it's gonna feel anxiety inducing in the moment. Just remember, this doesn't define you, and you guys you got this. You got this more than you realize. The more AP tests you take, the more you realize, the more you get this than you realize when you're taking the test.
Yeah, just go out there and have fun. Well, maybe some of you might not have fun with it.
Try and have fun.
Please do.
I still love the image of like someone doing like a really intense
Titration.
sitting at their exam, and everyone's like, maybe not stressed, but like focused, and they're just like ear to ear smiles, just having like
vibrating
the
with
time
excitement while
of
they're
their
writing down the
life.
processes.
I can imagine. I think I've done that on some tests where I just really loved the material.
Yeah, exactly.
Embrace
exactly.
it.
Like, I was taking the AP,
Love chemistry.
I was taking
You are
the AP
learning-
Bio exam, and I was having a good time with that exam. I was having a
Exactly,
really genuine good time.
same.
You
That was me
are
with
learning
stats.
the language of the universe out here, man. You are getting some serious power in learning chemistry. You understand how so much stuff works, even if you don't think it does.
Mhm.
So yeah.
Honestly, smiling through the test is pretty good advice. I think that's
It is.
actually solid. That's like get your endorphins up, you know?
What's my major? I'm a junior. I know everyone else here is a senior, so this is crazy. But I want to go into medicine too. I love medicine.
Yeah, let's go medicine, guys.
Yeah, me and Anuba both go to like allied health academy, so that's like crazy. I don't know, but we're not going to the same one. And we're both in New Jersey too, so that's crazy.
Yes, they.
All right, guys, we are in our last minute, so I just want to take a sec to say, have a good night or day, y'all. We'll see you guys tomorrow.